Of all the questions humanity has ever asked, perhaps none resonates more deeply within our souls than the simple wondering of how everything began. This question has echoed through countless generations, whispered around ancient campfires, debated in marble halls of philosophy, and now explored through the most sophisticated instruments ever created by human hands. The Big Bang represents our best scientific answer to this eternal question, and it has become one of the most profound ideas ever to emerge from the human mind. It tells us that everything we see, everything we touch, everything we love, and everything we dream about shares a common origin in a single moment of unimaginable energy and potential. Tonight, as you settle into comfort and let the weight of the day drift away, we will journey together through this remarkable story from its very first instant to the grand cosmic structures that fill the universe today. The Big Bang has woven itself into the fabric of modern culture in ways both obvious and subtle. When we speak of explosive beginnings or momentous starts, we often invoke its imagery without even realizing it. Television shows have borrowed its name, finding in those two simple words a perfect encapsulation of sudden dramatic origin. Scientists have become celebrities explaining its intricacies to fascinated audiences around the world. Children learn about it in school, their young minds stretching to comprehend timescales and temperatures that dwarf anything in everyday experience. The phrase itself has entered our common vocabulary, used to describe any sudden beginning or dramatic transformation. Yet beneath this cultural familiarity lies a story of extraordinary depth and beauty, one that most people have never fully heard. The journey toward understanding our cosmic origins stretches back through centuries of human curiosity and careful observation. Long before we had the mathematics or instruments to investigate the universe's beginning, humans looked up at the night sky and wondered. Ancient civilizations across every continent created stories to explain the existence of the stars, the sun, the moon, and the earth beneath their feet. The Babylonians spoke of primordial waters from which the gods emerged to shape reality. The ancient Egyptians described the universe rising from an infinite ocean of chaos called Nun. Hindu cosmology envisioned cycles of creation and destruction spanning billions of years, a concept that carries intriguing echoes of modern scientific thinking. Indigenous peoples around the world developed rich traditions explaining how the world came to be, each culture finding its own poetry in the mystery of existence. These ancient creation stories served profound purposes for the societies that told them. They provided frameworks for understanding humanity's place in the cosmos, offered moral guidance through divine narratives, and created shared cultural bonds through common origin stories. While modern science has given us a different kind of answer to the question of cosmic origins, we should appreciate these earlier attempts as expressions of the same fundamental wonder that drives cosmological research today. The human need to understand where we came from runs deep in our nature, and the Big Bang theory represents the latest chapter in this ancient quest for knowledge. The scientific story of the Big Bang began to take shape in the early 20th century, emerging from a remarkable convergence of theoretical insight and observational discovery. Albert Einstein published his general theory of relativity in 1915, providing humanity with a new understanding of gravity, space, and time. His equations described a universe that could expand or contract, though Einstein himself initially resisted this implication, adding a term called the cosmological constant to keep the universe static and unchanging. He would later call this one of his greatest mistakes, though, in a beautiful twist of scientific history, the cosmological constant has returned to modern cosmology in connection with dark energy. A few years after Einstein's breakthrough, a Belgian priest and physicist named Georges Lemaitre began exploring what the equations of general relativity truly implied. Lemaitre was a remarkable figure, equally devoted to his faith and his science, seeing no contradiction between the two. In 1927, he proposed that the universe was expanding, with galaxies moving apart from one another, like dots on the surface of an inflating balloon. He traced this expansion backward in time, reasoning that if the universe is growing larger today, it must have been smaller in the past. Following this logic to its ultimate conclusion, Lemaitre proposed that everything began from what he poetically called the primeval atom, a single point containing all the matter and energy that would become the cosmos we observe today. Lemaitre's ideas received crucial support from the observations of Edwin Hubble, the American astronomer whose name would later grace the famous space telescope. Working at the Mount Wilson Observatory in California, Hubble made meticulous measurements of distant galaxies throughout the 1920s. He discovered that the light from these galaxies was shifted toward the red end of the spectrum, a phenomenon that occurs when a light source is moving away from the observer. More remarkably, Hubble found that more distant galaxies showed greater redshifts, meaning they were receding faster. This relationship, now known as Hubble's law, provided powerful evidence that the universe was indeed expanding, just as Lemaitre had proposed. The term Big Bang itself came from an unexpected source. British astronomer Fred Hoyle, who actually opposed the theory and favoured an alternative model called the steady-state universe, coined the phrase during a BBC radio broadcast in 1949. Hoyle intended the name somewhat dismissively, but it captured the public imagination and stuck. There is a gentle irony in the fact that the theory's most famous name came from one of its critics, and Hoyle would spend much of his career arguing against the very idea he had inadvertently branded. The steady-state theory proposed that the universe had no beginning, with new matter continuously created to maintain a constant density as space expanded. For a time, this alternative commanded significant scientific support, and the debate between Big Bang and steady-state cosmology would not be decisively settled until the 1960s. The resolution came through one of the most important accidental discoveries in the history of science. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working with a large horn antenna at Bell Telephone Laboratories in New Jersey. They were trying to eliminate sources of noise from their equipment and kept detecting a persistent, low-level signal that seemed to come from every direction in the sky. No matter where they pointed their antenna, this faint microwave hiss remained constant. They even cleaned pigeon droppings from inside the horn, thinking the birds might somehow be responsible for the mysterious signal. What Penzias and Wilson had stumbled upon was the cosmic microwave background radiation, the afterglow of the Big Bang itself. This faint radiation had been predicted years earlier by physicists Ralph Alpher and Robert Herman, who calculated that the immense heat of the early universe should have left behind a detectable signal, now cooled by billions of years of cosmic expansion. The discovery of the cosmic microwave background provided stunning confirmation of the Big Bang theory, showing that our universe did indeed emerge from an extremely hot, dense state. Penzias and Wilson received the Nobel Prize in Physics for their discovery, and the cosmic microwave background has since become one of the most important tools in modern cosmology. Since those pioneering days, our understanding of the Big Bang has grown enormously richer and more detailed. Space telescopes and ground-based observatories have mapped the cosmic microwave background with exquisite precision, revealing tiny temperature fluctuations that would eventually grow into galaxies and galaxy clusters. Particle accelerators have recreated conditions similar to those in the early universe, allowing physicists to study the behavior of matter at extreme energies. Theoretical advances have extended our understanding back to the tiniest fractions of a second after the beginning, though mysteries remain at the very earliest moments where our current physics breaks down. The Big Bang Theory has also raised profound philosophical questions that continue to inspire debate and wonder. What caused the Big Bang to happen? What, if anything, existed before it? Is our universe the only one, or might it be part of a larger multiverse? These questions push against the boundaries of what science can currently answer, venturing into territory where physics, philosophy, and perhaps even theology intersect. Different thinkers have approached these questions in different ways, and there is something beautiful in the fact that our most successful scientific theory of cosmic origins still leaves room for mystery and wonder. As you listen tonight, letting these ideas wash over you like gentle waves, know that you're participating in one of humanity's greatest intellectual adventures. The story of the Big Bang is not just a collection of facts and figures, though it contains plenty of those. It is a narrative of discovery and wonder, of human minds reaching out to comprehend the incomprehensible. It connects us to the ancient stargazers who first wondered about the heavens, and to the future generations who will continue to explore the cosmos long after we are gone. In understanding where the universe came from, we come to understand something profound about ourselves and our place in the grand cosmic story. Section 2, Before the Beginning, What Existed Before? As we settle deeper into our journey through cosmic history, we encounter a question that has puzzled philosophers, theologians, and scientists alike for as long as humans have contemplated origins. What existed before the Big Bang? This question seems so natural, so obvious, that it might surprise you to learn that it may not have a meaningful answer in the way we normally understand such things. The very concepts of before and after, which feel so fundamental to our everyday experience, may not apply to the moment of creation itself. Let us explore this profound mystery together, gently and without rushing, allowing the ideas to unfold at their own peaceful pace. To understand why the question of before the Big Bang is so tricky, we need to think carefully about the nature of time itself. In our daily lives, time feels like a river flowing steadily forward, carrying us from past to present to future. We remember yesterday, experience today, and anticipate tomorrow. This intuitive sense of time as something that simply exists, independent of everything else, dominated human thinking for thousands of years. Even the great physicist Isaac Newton, whose laws of motion governed our understanding of the physical world for centuries, believed in absolute time, a cosmic clock ticking away uniformly throughout the universe. Einstein's theories of relativity fundamentally changed our understanding of time. He showed that time is not absolute but relative, flowing at different rates depending on how fast you are moving or how strong the gravitational field around you happens to be. Astronauts on the International Space Station age slightly slower than people on Earth's surface, and clocks run measurably slower near massive objects like planets and stars. These effects are tiny in everyday circumstances, but become dramatic in extreme environments. Near a black hole, time slows so profoundly that an outside observer would see someone falling in appear to freeze at the event horizon, never quite crossing over. Even more remarkably, Einstein showed that time and space are not separate entities, but woven together into a single fabric called space-time. This four-dimensional structure, with 3 dimensions of space and 1 of time, can be bent and curved by the presence of matter and energy. What we experience as gravity is actually the curvature of space-time, with objects following the straightest possible paths through this curved geometry. A planet orbits a star not because some invisible force pulls it, but because the star's mass warps space-time, and the planet follows the curved contours of that warping. This understanding of time as part of space-time, rather than as an independent backdrop against which events unfold has profound implications for thinking about the Big Bang. According to most interpretations of the standard cosmological model, time itself began with the Big Bang. There was no before because there was no time in which a before could exist. The question of what happened before the Big Bang is a bit like asking what is north of the North Pole. The question seems grammatically correct, but it refers to something that does not exist. Just as you cannot travel north from the northernmost point on Earth, you cannot travel backward in time to before time began. This idea can feel deeply unsatisfying to our human minds, which are so accustomed to thinking in terms of cause and effect, of events following one another in orderly sequence. We want to know what caused the Big Bang, what set it in motion, what existed in the moment before everything began. The notion that there simply was no such moment challenges our most basic intuitions about how reality works. Yet this is precisely what the mathematics of general relativity suggests when we trace the expansion of the universe backward to its apparent origin. However, we should approach this conclusion with appropriate humility. The equations of general relativity break down at the very beginning, at the point physicists call the singularity. A singularity is a place where the mathematics produces infinite values, quantities that cannot correspond to physical reality. When we encounter infinities in our equations, it usually means we have pushed our theory beyond its domain of validity, that we need new physics to describe what is actually happening. The singularity at the Big Bang may not be a real feature of the universe, but rather a sign that general relativity is incomplete, that a more fundamental theory is needed to describe the earliest moments of cosmic history. The search for this more fundamental theory has led physicists to explore the interface between general relativity and quantum mechanics, the two pillars of modern physics. General relativity describes gravity and the large-scale structure of space-time, while quantum mechanics governs the behavior of matter and energy at the smallest scales. Both theories have been tested with extraordinary precision and have never been found wanting within their respective domains. Yet they seem fundamentally incompatible with each other, using different mathematical frameworks and making different assumptions about the nature of reality. A theory of quantum gravity, which would unite these two great frameworks, remains one of the most sought-after goals in theoretical physics. String theory, loop quantum gravity, and other approaches have made progress toward this goal, but none has yet achieved the status of an established, experimentally verified theory. Until we have a working theory of quantum gravity, our understanding of the very earliest moments of the universe, the first tiny fraction of a second when quantum effects and gravitational effects were both important, will remain incomplete. Some approaches to quantum gravity suggest intriguing possibilities for what might have preceded the Big Bang. Loop quantum gravity, for example, replaces the classical singularity with a quantum bounce. In this picture, the universe did not emerge from nothing but rather from a previous contracting phase that reached a minimum size and then began expanding. The Big Bang becomes the Big Bounce, a transition point rather than an absolute beginning. If this view is correct, our universe might be just one in an endless series of cosmic cycles, each bounce giving rise to a new expanding phase that eventually contracts and bounces again. Another possibility comes from the concept of eternal inflation, which emerges from certain versions of inflationary cosmology. In this picture, inflation, the period of extremely rapid expansion that we will explore in detail later, never completely ends. While it stops in some regions, allowing those regions to develop into universes like our own, it continues forever in other regions, constantly spawning new bubble universes. Our observable universe would be just one bubble in an infinite, eternally inflating sea, and the question of what came before our Big Bang would be answered by pointing to the larger inflationary multiverse from which our bubble emerged. The multiverse concept appears in several different forms in modern cosmology and physics. Beyond eternal inflation, string theory suggests the existence of a vast landscape of possible universes, each with different physical constants and laws. Some physicists have proposed that new universes might be born inside black holes, with the singularity at a black hole's centre serving as the seed for a new spacetime. These ideas remain highly speculative, and it is important to acknowledge that we currently have no way to test them observationally. They represent the frontier of theoretical speculation, places where imagination and mathematics venture beyond what experiments can currently verify. The concept of nothing itself becomes surprisingly complex when examined closely. In everyday language, nothing simply means the absence of anything, empty space with no objects in it. But physicists have learned that empty space, the vacuum, is far from empty in the quantum mechanical sense. The vacuum seethes with activity, with pairs of virtual particles constantly popping into existence and annihilating each other, their brief lives permitted by the uncertainty principle of quantum mechanics. This quantum vacuum has measurable effects, such as the Casimir force between closely spaced metal plates, confirming that empty space is anything but truly empty. Some cosmologists have proposed that the universe might have emerged from a quantum fluctuation in a primordial vacuum, a nothing that was not truly nothing, but rather a state of quantum potential. In this view, the laws of quantum mechanics permit the spontaneous appearance of spacetime and matter-energy from what might loosely be called nothing, though this nothing already contains the quantum fields and physical laws that make such an appearance possible. The philosopher and physicist may debate whether this truly counts as creation from nothing or whether it merely pushes the question back a step, but it offers a framework in which the universe's existence becomes less mysterious, or at least differently mysterious. The question of why there is something rather than nothing, which the philosopher Gottfried Wilhelm Leibniz called the first question that should rightly be asked, remains unanswered by physics. Science can describe how the universe evolved from its earliest moments, can trace the history of matter and energy through billions of years of cosmic development, but it cannot explain why there is a universe at all, rather than simply nothing. This question may lie beyond the reach of scientific inquiry, belonging instead to the domain of philosophy or theology, or perhaps future discoveries will reveal aspects of reality we cannot currently imagine, shedding new light on this deepest of mysteries. As you rest and let these ideas settle gently into your mind, there is no need to grasp them all firmly or to resolve every question. The mystery of what came before the Big Bang, if anything did, is one that the greatest minds of our species continue to ponder. It is enough to appreciate the depth of the question, to feel the wonder that arises when we contemplate the origin of everything. Whether the universe emerged from a quantum fluctuation, bounced from a previous cosmic cycle, bubbled out of an eternal inflationary sea, or began in some way we have not yet imagined, the fact that we can ask these questions at all is itself a kind of miracle. The boundary of our knowledge is not a wall but a horizon, and horizons have a way of receding as we approach them. Each answer we find reveals new questions. Each mystery solved opens doors to deeper mysteries. This is the nature of scientific inquiry, an endless adventure of discovery that stretches before us like the universe itself. And just as the universe appears to have no edge, no boundary beyond which there is nothing, so too does our quest for understanding extend without limit into the unknown. For now, let us accept that the question of before the Big Bang remains open, a space for wonder and speculation rather than certainty. As we continue our journey through cosmic history, we will move from this realm of deep uncertainty into territory where our knowledge becomes progressively more secure. The story of the universe from its first fraction of a second onward is one we can tell with increasing confidence, supported by observation and experiment. But we carry with us the awareness that even our most complete understanding rests upon foundations that remain, in some ultimate sense, mysterious. The night sky above us, if we could see it now, contains light that has travelled for billions of years to reach our eyes. Some of that light began its journey when the universe was young, when galaxies were just beginning to form, when the cosmic story was still in its opening chapters. By studying this ancient light, we peer back through time toward the beginning, approaching ever closer to that first moment without ever quite reaching it. The universe keeps its deepest secrets well, but it has revealed enough to fill us with awe and gratitude for the chance to witness its grandeur. Let your breathing slow and deepen as we prepare to venture into the first moments of cosmic time. The questions we have explored in this section will remain with us as a kind of background music, a reminder of the profound mystery that underlies everything we will discuss. But now we turn our attention to what we can say with greater confidence, to the story that begins at the very first instant of time as we understand it, when the universe was unimaginably hot, unimaginably dense, and unimaginably small. This is the story of the Planck epoch, the first heartbeat of creation, and it awaits us just ahead. Section 3. The Planck epoch, the first moment of time. We arrive now at the very threshold of existence, the first conceivable moment of cosmic time. This is the Planck epoch, named after the German physicist Max Planck, who laid the foundations of quantum mechanics in the early 20th century. The Planck epoch represents the earliest period we can even attempt to describe using our current understanding of physics, and it lasted for an almost inconceivably brief span. From the moment of the Big Bang until approximately 10 to the negative 43 seconds afterward, the universe existed in a state so extreme, so far removed from anything in our everyday experience, that our most fundamental theories of physics cannot fully describe it. Let us explore this mysterious beginning together, gently and without haste, allowing the strangeness of these ideas to wash over us like a warm, enveloping mist. To appreciate just how brief the Planck epoch was, we need to develop some sense of the timescales involved. 10 to the negative 43 seconds is a decimal point followed by 42 zeros and then a 1. Written out fully, it would look like this: 0, oro duo, doron seconds. This is not merely a short time by human standards, it is a short time by any standard we can meaningfully conceive. The fastest events we encounter in everyday life, like the flash of a camera or the blink of an eye, last for thousandths or hundredths of a second. The fastest processes studied in chemistry occur on timescales of femtoseconds, which are millionths of a billionth of a second. Even the quickest nuclear reactions happen over timescales that are enormously long compared to the Planck time. The Planck time is not simply an arbitrary small number chosen for convenience. It emerges naturally from the fundamental constants of physics when we combine quantum mechanics and gravity. Max Planck discovered that by combining three fundamental constants, the speed of light, the gravitational constant, and the quantum of action that now bears his name, he could derive natural units of length, time, and mass. These Planck units represent the scales at which quantum gravitational effects become important, where the smooth fabric of space-time described by general relativity gives way to something far stranger and less well understood. The Planck length, approximately 1.6 times 10 to the negative 35 meters, is the smallest length scale that has physical meaning in our current theories. Below this scale, the very concept of distance becomes fuzzy and ill-defined. The Planck mass, about 22 micrograms, might seem surprisingly large compared to the masses of subatomic particles, but it represents the mass energy at which quantum gravitational effects become dominant. And the Planck time, that impossibly brief 10 to the negative 43 seconds, is the time it takes light to travel 1 Planck length. It represents the smallest meaningful unit of time, the finest grain of the temporal fabric. During the Planck epoch, the entire observable universe, everything that would eventually become hundreds of billions of galaxies containing hundreds of billions of stars each, was compressed into a region smaller than the Planck length. The density of matter and energy was so extreme that it exceeded anything we can produce in our most powerful particle accelerators by factors that beg a description. The temperature was approximately 10 to the 32 degrees Kelvin, a number so large that comparisons to familiar temperatures become meaningless. The core of the Sun, at about 15 million degrees, is frigid beyond measure compared to the Planck temperature. Even the temperatures achieved in particle collider experiments, hot enough to melt protons into their constituent quarks, represent mere lukewarm conditions compared to the searing intensity of the Planck epoch. At these extreme conditions, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are believed to have been unified into a single force. In our everyday experience and in all experiments we have conducted, these forces appear distinct, each with its own characteristics and strength. Gravity holds planets in orbit and keeps our feet on the ground. Electromagnetism governs light, chemistry, and the behavior of charged particles. The strong force binds quarks together inside protons and neutrons and holds atomic nuclei together against the electromagnetic repulsion of their positively charged protons. The weak force governs certain types of radioactive decay and plays a crucial role in the nuclear reactions that power the Sun. The idea that these seemingly different forces might be aspects of a single underlying force has been one of the great themes of physics over the past century. In the 1960s and 70s, physicists succeeded in unifying electromagnetism and the weak force into the electroweak force, showing that at sufficiently high energies, these two forces become indistinguishable. This unification was confirmed experimentally with the discovery of the W and Z bosons, the carrier particles of the weak force, at CERN in the 1980s. The physicists who developed the electroweak theory, Sheldon Glashow, Abdus Salam, and Steven Weinberg, received the Nobel Prize for this achievement. The next step in unification, combining the electroweak force with the strong force, remains an active area of research. Grand unified theories, or GUTS, attempt to describe how these forces merge at even higher energies that existed in the universe just after the Planck epoch ended. We will explore these theories in more detail in the next section. But at the Planck scale, even grand unification is not enough. Gravity, which has stubbornly resisted incorporation into the quantum framework that describes the other forces, must also join the unified picture. A complete theory of everything, sometimes called quantum gravity or a theory of everything, would describe all four forces as manifestations of a single underlying principle. We do not yet possess such a theory, though many brilliant minds have devoted their careers to finding one. String theory, which proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings of energy, offers one promising approach. Loop quantum gravity, which attempts to quantize spacetime itself, provides another. Other approaches, such as causal set theory and asymptotic safety, explore different mathematical frameworks. Each of these approaches has achieved partial successes and faced significant challenges, and it remains unclear which, if any, will ultimately prove correct. The absence of a complete theory of quantum gravity means that our understanding of the Planck epoch is necessarily incomplete and speculative. We can describe the conditions that must have prevailed, the temperatures and densities and energies involved, but we cannot say with confidence exactly what was happening at the most fundamental level. The equations of general relativity, when pushed back to the Planck time, produce singularities, infinite values that signal the breakdown of the theory. Quantum mechanics, for its part, was not designed to handle the extreme gravitational effects present at the Planck scale. We are like explorers approaching an uncharted territory, able to see its outline from a distance, but unable to map its interior until we develop better tools. Despite these limitations, physicists have made educated guesses about the nature of the Planck epoch, based on the properties that any successful theory of quantum gravity must possess. One common expectation is that space-time itself becomes quantized at the Planck scale, breaking up into discrete units rather than forming a smooth continuum. Just as matter, which appears continuous to our eyes, is actually made of atoms, and just as light, which seems to flow smoothly, is actually composed of discrete photons, so too might space and time be granular at the smallest scales. This quantum foam, as it is sometimes called, would be a seething, turbulent structure with geometry fluctuating wildly from moment to moment and place to place. In this picture, the familiar concepts of space and time lose their meaning at the Planck scale. There is no smooth background against which events unfold, no orderly progression from past to future. Instead, there is a chaotic quantum soup in which space and time are themselves dynamic, fluctuating quantities. Tiny wormholes might form and disappear, connecting distant points of space for brief instants. The topology of space, the way different regions connect to one another, might change from moment to moment. Causality itself, the principle that causes precede their effects, might become blurred or undefined. These ideas remain highly speculative, and different approaches to quantum gravity paint different pictures of Planck-scale physics. Some theories suggest that space has a minimum length, a smallest possible distance that cannot be subdivided further. Others propose that time might be emergent, arising from more fundamental quantum processes rather than existing as a basic feature of reality. Still others suggest that the number of spatial dimensions might be different at the Planck scale than at larger scales, with extra dimensions becoming apparent only at extremely small distances. The Planck epoch ended when the universe had expanded and cooled enough for gravity to separate from the other forces, becoming the distinct interaction we observe today. This separation, sometimes called symmetry breaking, is a concept we will explore more fully in the next section. For now, it is enough to understand that the unified force of the Planck epoch began to differentiate, with gravity going its own way, while the other three forces remained unified for a while longer. The universe was still unimaginably hot and dense by any ordinary standard, but it had cooled enough for the first distinct structures to begin emerging from the primordial unity. As you rest and let these ideas settle into your consciousness, there is no need to fully comprehend every detail. The Planck epoch lies at the very edge of human understanding, a realm where our best theories falter and our intuitions fail. What matters is not mastering the mathematics, but appreciating the profound strangeness of those first moments. The way the familiar categories of space and time and force dissolve into something more fundamental and mysterious. The universe began in a state we can barely imagine, and from that unimaginable beginning, everything we know and love eventually emerged. The Planck epoch lasted for only the briefest instant, yet it set the stage for everything that followed. The laws of physics that govern our universe today, the constants that determine the strength of forces, and the masses of particles were somehow encoded in that first moment. Whether these laws and constants were fixed by some deeper principle, selected from a vast landscape of possibilities, or simply brute facts with no further explanation, remains one of the deepest questions in physics and philosophy. The Planck epoch is where these questions have their origin, even if their answers remain elusive. Think of the Planck epoch as the first brushstroke on a cosmic canvas, the initial gesture from which the entire painting would develop. It contained within itself all the potential for stars and galaxies, for planets and oceans, for life and consciousness. The complexity and beauty of the universe we observe today were present in embryonic form in that first instant, waiting to unfold through billions of years of cosmic evolution. From the quantum foam of the Planck epoch to the spiral arms of the Milky Way, from the first fluctuations in the unified field to the neurons firing in your brain, as you listen to these words, there is an unbroken chain of development stretching back to the very beginning. Let your mind rest now on the threshold of time, contemplating that first moment without straining to understand it fully. The universe has been generous in revealing its secrets, but it has also preserved some mysteries, perhaps forever. The Planck epoch is one of those mysteries, a reminder that even our most powerful theories have limits, that there are depths to reality we have not yet plumbed. And in that mystery, there is a kind of comfort, a sense that the cosmos is vast enough to always contain more than we can know, more than we can imagine, more than we can dream. Section 4, the grand unified epoch and symmetry breaking. Following the ineffable mystery of the Planck epoch, the universe entered a new phase of its existence, one that remains extremely speculative but slightly more accessible to our current theories. This is the grand unified epoch, lasting from approximately 10 to the negative 43 seconds until about 10 to the negative 36 seconds after the Big Bang. During this period, gravity had separated from the other forces, but electromagnetism, the strong force and the weak force, remained unified in a single grand unified force. The temperatures were still staggering, around 10 to the 28 degrees Kelvin, and the energies involved exceeded anything we can produce in our laboratories. Yet this epoch represents a crucial transition in cosmic history, the first step in the differentiation of forces that would eventually give rise to the rich variety of physical phenomena we observe today. The concept of grand unification emerged in the 1970s as physicists sought to extend the success of electroweak unification. If the electromagnetic and weak forces could be shown to be aspects of a single electroweak force, perhaps all three non-gravitational forces could be unified at even higher energies. Grand unified theories, commonly abbreviated as GUTS, attempt to describe this deeper unification, proposing mathematical frameworks in which the strong, weak, and electromagnetic forces emerge from a single underlying interaction. Several different grand unified theories have been proposed, each with its own mathematical structure and predictions. The simplest, known as the Georgi-Glashow model, or SU5 GUT, was developed in 1974. It predicted that protons, normally considered stable particles, should occasionally decay into lighter particles with a half-life of around 10 to the 31st years. This is an enormously long time, far longer than the current age of the universe, but experiments with large tanks of water surrounded by sensitive detectors could potentially observe such decays if enough protons were monitored for long enough. Despite decades of searching, no proton decay has ever been observed, ruling out the simplest versions of grand unification and pushing physicists toward more complex models. Other grand unified theories based on larger symmetry groups with names like SO10 and E6 remain viable and make different predictions about proton decay and other phenomena. These theories are mathematically elegant and offer tantalizing hints of deeper structure in the laws of physics. They predict the existence of new particles, extremely massive and unstable, that would have existed in the grand unified epoch, but decayed away long ago. Some of these particles, called X and Y bosons, would have had the remarkable property of mediating interactions that change quarks into leptons, and vice versa, processes forbidden by the separate conservation laws of the strong and electroweak forces. The grand unified epoch ended with another symmetry breaking event, in which the grand unified force split into the strong force on one hand and the electro-weak force on the other. This transition, like the earlier separation of gravity, was not a gradual change, but a sudden phase transition, similar in some ways to water freezing into ice or steam condensing into liquid. As the universe cooled below a critical temperature, the symmetric state became unstable, and the forces differentiated into their distinct identities. Symmetry breaking is a profound concept that appears throughout physics, from the behavior of magnets to the properties of superconductors to the origin of particle masses. To understand it, imagine a ball balanced perfectly on top of a smooth hill. This situation is symmetric. The ball could roll in any direction, and all directions are equivalent. But this symmetric state is unstable. The slightest perturbation will cause the ball to roll down in some particular direction, breaking the symmetry. Once the ball has rolled down, the symmetry is hidden. An observer who sees only the ball at the bottom of the hill might not realize that the underlying laws governing the ball are perfectly symmetric. In the early universe, the extreme temperatures provided enough energy to keep the forces unified, like the ball balanced on top of the hill. As the universe cooled, this symmetric state became unstable, and the forces rolled down into their distinct identities. The symmetry is still present in the underlying laws of physics, but it is hidden from us because we live in a universe that has cooled far below the unification temperature. Only by recreating the extreme conditions of the early universe, in particle accelerators or through careful theoretical analysis, can we glimpse the hidden symmetry that underlies the apparent diversity of forces. The symmetry breaking at the end of the grand unified epoch may have had dramatic consequences for the universe. One important possibility is that it triggered cosmic inflation, the period of exponential expansion that we will explore in detail in the next section. The energy released during the phase transition could have driven space to expand at an astonishing rate, stretching the universe by a factor of at least 10 to the 26 in a tiny fraction of a second. This inflationary expansion would solve several puzzles about the observed universe and leave subtle imprints that we can detect today. Another consequence of grand unified symmetry breaking involves the origin of matter itself. One of the deepest mysteries in cosmology is why the universe contains matter at all. According to our best understanding of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other, converting their mass into pure energy. If the early universe had contained exactly equal amounts of matter and antimatter, all of it would have annihilated, leaving a universe filled with radiation, but no atoms, no stars, no planets, no life. Obviously, this did not happen. The universe we observe is made almost entirely of matter, with only trace amounts of antimatter produced in high-energy processes. Something must have tipped the balance, creating a slight excess of matter over antimatter. For every billion antimatter particles, there must have been 1,000,000,001 matter particles. When the annihilation was complete, that tiny excess remained, and it is from that excess that everything we see is made. You and the planet you live on, and the stars in the sky are all descendants of that primordial imbalance. Grand unified theories offer a possible explanation for this matter: antimatter asymmetry, a process called baryogenesis. The X and Y bosons predicted by these theories could decay in ways that produce slightly more matter than antimatter, provided certain conditions are met. These conditions, identified by the physicist Andrei Sakharov in 1967, include violation of a symmetry called CP, charge parity symmetry, and departure from thermal equilibrium. The symmetry breaking at the end of the grand unified epoch could have provided exactly the right conditions for baryogenesis to occur, explaining why we live in a universe of matter rather than radiation. The grand unified epoch also saw the production of exotic objects called magnetic monopoles. These hypothetical particles would be like magnets with only one pole, either north or south, but not both. In ordinary magnets, if you cut a bar magnet in half, you get two smaller magnets, each with its own north and south pole. You can never isolate a single magnetic pole, but grand unified theories predict that magnetic monopoles should have been produced copiously during the symmetry breaking transition, created as defects in the fabric of space where the symmetry broke in different directions in adjacent regions. The prediction of magnetic monopoles created a puzzle for cosmology. If monopoles were produced as abundantly as simple calculation suggested, they should dominate the mass of the universe today, making it look completely different from what we observe. This monopole problem was one of the motivations for the development of inflationary theory. As we will see, inflation provides an elegant solution by diluting any monopoles produced before or during inflation to negligible densities. As the grand unified epoch drew to a close, the universe had taken its first steps toward the differentiated state we observe today. Gravity had already separated during the Planck epoch, and now the strong force went its own way, leaving the electro-weak force still unified. The temperature had dropped to around 10 to the 27 degrees Kelvin, still unimaginably hot, but cool enough for the strong force to assert its independence. The stage was set for the next great transformation, the inflationary epoch that would shape the large-scale structure of the cosmos. Throughout this period, the universe remained far too hot and dense for any familiar forms of matter to exist. There were no atoms, no protons, no neutrons, not even the quarks that would eventually combine to form these particles. Instead, there was a seething plasma of exotic particles and radiation, a soup of energy and matter in forms we can barely imagine. The particles that existed were constantly being created and destroyed, popping into existence from the intense energy of the environment and annihilating back into radiation moments later. Yet within this chaos, the seeds of order were being planted. The symmetry breaking events that occurred during this epoch determined the strengths of the forces, the masses of the particles, and the rules governing their interactions. These parameters, set in the first tiny fraction of a second, would shape the entire subsequent history of the universe. The fact that atoms can exist, that stars can shine, that chemistry can happen, that life can emerge, all of this was determined by what happened during the grand unified epoch and its aftermath. The grand unified epoch reminds us that the apparent complexity of the physical world may arise from simpler underlying principles. The diversity of forces and particles we observe today may be like the diversity of snowflakes, each one different in detail, but all arising from the same basic physics of water crystallization. At the highest energies, the deepest level of description, there may be a beautiful simplicity that our low-energy perspective obscures. The quest to understand this underlying unity has driven physics for over a century and continues to inspire researchers today. As you drift deeper into relaxation, let the concept of symmetry breaking settle gently into your awareness. The universe began in a state of perfect symmetry, all forces unified, all possibilities equal. As it cooled, this symmetry broke, and the rich diversity of the physical world emerged. There is something poetic in this picture, a cosmic story of unity giving way to diversity, of potential becoming actual, of the one becoming the many. And yet the unity is never truly lost. It remains encoded in the deep structure of physical law, waiting to be rediscovered by minds curious enough to seek it. The grand unified epoch lasted for only about 10 to the negative 36 seconds, a duration so brief that it makes the Planck epoch seem almost leisurely by comparison. Yet in that fleeting interval, the universe underwent transformations of profound significance. The strong force separated from its siblings, magnetic monopoles may have formed, the seeds of matter-antimatter asymmetry may have been planted, and the conditions for inflation may have been established. From our perspective, billions of years later, these events seem almost instantaneous, but they set the course for everything that would follow. We stand now at the threshold of the inflationary epoch, one of the most dramatic and important periods in cosmic history. The universe is about to undergo an expansion of almost incomprehensible magnitude, growing from something smaller than an atom to something larger than the observable universe today, all in a fraction of a second. This inflationary expansion will smooth out irregularities, flatten the geometry of space, dilute unwanted relics like magnetic monopoles, and plant the quantum seeds that will eventually grow into galaxies and clusters of galaxies. It is a remarkable story, and it awaits us just ahead. For now, let your breathing slow and your body relax as we pause at this threshold. The universe has journeyed from the ineffable mystery of the Planck epoch through the grand unified epoch, and it is about to enter a new phase of explosive growth. The forces have begun to differentiate, the symmetries have begun to break, and the stage is set for the next act in the cosmic drama. Rest here for a moment, in this brief pause between epochs, and prepare yourself for the astonishing story of inflation. Section 5. Inflation, the universe's exponential expansion. We arrive now at one of the most extraordinary chapters in the story of our universe, a period so dramatic and transformative that it reshapes our entire understanding of cosmic origins. This is the epoch of inflation, a brief but spectacular phase during which the universe expanded at a rate that defies ordinary comprehension. In a tiny fraction of a second, space itself stretched by a factor so enormous that the numbers we use to describe it lose all connection to everyday experience. The inflationary epoch solved profound puzzles about the observed universe, explained features that had seemed deeply mysterious, and planted the seeds from which all cosmic structure would eventually grow. Let us explore this remarkable period together, gently and without rushing, allowing the grandeur of these ideas to unfold at their own peaceful pace. The story of inflation begins not in the early universe, but in the minds of physicists struggling to understand puzzling features of the cosmos we observe today. By the late 1970s, the Big Bang theory had achieved remarkable success in explaining many aspects of the universe, from the cosmic microwave background radiation to the abundance of light elements. Yet several features of the observed universe seemed deeply puzzling, requiring extremely special initial conditions that cried out for explanation. These puzzles, known as the horizon problem, the flatness problem, and the monopole problem, would find their resolution in the bold idea of cosmic inflation. The horizon problem arises from a simple observation about the cosmic microwave background radiation. This ancient light, released when the universe was about 380,000 years old, has almost exactly the same temperature in every direction we look, varying by only a few parts in 100,000. This uniformity might seem natural, the kind of thing we would expect from a universe that started in thermal equilibrium. But there is a deep puzzle hidden in this apparent simplicity. Consider 2 points on opposite sides of the sky, separated by the maximum possible distance we can observe. Light from these points has been travelling toward us since the cosmic microwave background was released, and it has only just now reached us. This means that light from one of these points has not yet had time to reach the other point. In the language of physics, these regions have never been in causal contact. They have never been able to exchange information, energy, or anything else. How, then, did they come to have exactly the same temperature? It would be like 2 people on opposite sides of the Earth who have never communicated in any way, somehow deciding to wear exactly the same outfit on the same day. Without some mechanism to coordinate their states, such agreement seems impossibly coincidental. The flatness problem concerns the geometry of space on the larger scales. According to general relativity, space can be curved in different ways depending on the density of matter and energy it contains. If the density is above a critical value, space curves back on itself like the surface of a sphere, and the universe is said to be closed. If the density is below the critical value, space curves like a saddle and the universe is open. Only if the density equals the critical value exactly is space flat, extending infinitely in all directions without curving. Observations indicate that our universe is very close to flat, with a density extremely close to the critical value. This might seem like a natural state of affairs, but the equations of cosmology reveal something surprising. The flatness of the universe is unstable over time. If the early universe had been even slightly more dense than critical, the excess would have grown over time, causing the universe to collapse long ago. If it had been slightly less dense, the deficit would have grown, causing the universe to expand so rapidly that galaxies could never have formed. For the universe to be as close to flat as we observe today, it must have been flat to an extraordinary precision in the early universe, to within about 1 part in 10 to the 60. Such fine-tuning demands explanation. The monopole problem, which we touched upon in the previous section, concerns the exotic magnetic monopoles predicted by grand unified theories. These theories suggest that monopoles should have been produced copiously during the symmetry breaking at the end of the grand unified epoch. Simple calculations indicate that monopoles should be so abundant that they would dominate the mass of the universe, making it look completely different from what we observe. Yet no magnetic monopole has ever been detected, despite extensive searches. Where did all the monopoles go? In 1979 and 1980, a young physicist named Alan Guth was pondering these puzzles while working at the Stanford Linear Accelerator Center. Guth was not a cosmologist by training, but a particle physicist interested in grand unified theories and their implications. As he worked through the consequences of these theories for the early universe, he had a remarkable insight that would transform our understanding of cosmic origins. Guth proposed that the early universe underwent a brief period of exponential expansion, driven by a peculiar form of energy associated with a quantum field he called the inflaton. During this inflationary epoch, space expanded by at least a factor of 10 to the 26, and possibly much more, in a time interval of roughly 10 to the negative 32 seconds. This expansion was not the ordinary expansion of the Big Bang, in which matter and radiation spread out through existing space. Instead, it was an expansion of space itself, with new space being created between every pair of points, stretching the fabric of the cosmos at a rate far exceeding the speed of light. The idea that space could expand faster than light might seem to violate Einstein's theory of relativity, which establishes the speed of light as a cosmic speed limit. But this limit applies only to objects moving through space, not to the expansion of space itself. During inflation, no particle or signal travelled faster than light through its local region of space. Instead, the space between particles stretched so rapidly that distant regions were carried apart at superluminal rates. This distinction is subtle but crucial, and it allows inflation to occur without violating any known laws of physics. Inflation elegantly solves all three of the puzzles that motivated its invention. The horizon problem dissolves because regions that appear causally disconnected today were actually in close contact before inflation began. The entire observable universe, and much more beyond, originated from a tiny patch of space, small enough for light to cross many times over. This patch had plenty of time to reach thermal equilibrium, achieving the uniform temperature we observe. Inflation then stretched this tiny uniform patch to cosmic scales, explaining why the cosmic microwave background looks the same in every direction. The flatness problem resolves because inflation drives the universe toward flatness regardless of its initial curvature. Imagine drawing a small circle on the surface of a balloon and then inflating the balloon enormously. No matter how curved the balloon was initially, the region inside your circle becomes flatter and flatter as the balloon expands. In the same way, inflation stretched space so dramatically that any initial curvature was smoothed away, leaving the universe extremely close to flat. The fine-tuning that seemed so puzzling becomes a natural consequence of inflationary dynamics. The monopole problem finds its solution in the dilution that inflation provides. Any magnetic monopoles produced before or during the early stages of inflation would be spread across an enormously larger volume of space, reducing their density to negligible levels. The monopoles are not destroyed but simply diluted, like a drop of ink dispersed through an ocean. After inflation, the universe reheats and produces new particles, but the conditions are no longer right for monopole production. The monopoles that grand unified theories predict are still out there somewhere, but they are so rare that we would be extraordinarily lucky to ever encounter one. The mechanism driving inflation involves a quantum field called the inflaton, though the precise identity of this field remains unknown. In the simplest models, the inflaton field starts in a high-energy state, far from its minimum energy configuration. Like a ball perched high on a hill, the field wants to roll down to its lowest energy state, but the shape of the energy landscape causes it to roll very slowly. While the field is rolling slowly, it behaves like a cosmological constant, a form of energy that fills space uniformly and drives exponential expansion. This slow roll continues until the field approaches its minimum, at which point it begins to oscillate rapidly around the lowest energy state. These oscillations transfer the energy stored in the inflaton field to other particles, reheating the universe and producing the hot, dense plasma that would characterize the subsequent epochs. The end of inflation is not a gradual tapering off, but a relatively sudden transition, sometimes called reheating or preheating, that marks the beginning of the hot Big Bang in its traditional sense. Different models of inflation propose different shapes for the inflaton potential. The mathematical function describing how the field's energy depends on its value. Some models feature a plateau at high energies, allowing for slow roll over an extended period. Others involve a field slowly climbing a gentle slope before rolling down the other side. Still others invoke multiple fields interacting in complex ways. These different models make different predictions for observable quantities, and cosmologists have worked hard to distinguish between them using precise measurements of the cosmic microwave background and other observations. One of the most remarkable aspects of inflation is its ability to explain the origin of cosmic structure. The universe we observe today is not perfectly uniform, but contains galaxies, clusters of galaxies, and vast cosmic voids arranged in a complex web of structure. This structure grew from tiny seed fluctuations present in the early universe, fluctuations that were amplified by gravity over billions of years. But where did these seed fluctuations come from? Inflation provides a stunning answer. They arose from quantum fluctuations in the inflaton field itself. Quantum mechanics tells us that no field can be perfectly uniform. There are always tiny, random fluctuations arising from the uncertainty principle. During inflation, these quantum fluctuations were stretched to macroscopic scales by the exponential expansion, becoming frozen into the fabric of space as classical density perturbations. Regions with slightly higher density would eventually attract more matter through gravity, growing into galaxies and clusters, while regions with slightly lower density would become the cosmic voids. This quantum origin of cosmic structure is one of the most profound connections in all of physics, linking the smallest scales governed by quantum mechanics to the largest scales of cosmic architecture. The galaxies we see scattered across the night sky, including our own Milky Way, trace their origins back to quantum fluctuations during inflation. The very ground beneath your feet, the atoms in your body, the thoughts in your mind, all owe their existence to quantum events that occurred in the first fraction of a second after the Big Bang. The fluctuations produced by inflation have specific statistical properties that can be tested observationally. They should be nearly scale invariant, meaning that fluctuations of different sizes have nearly the same amplitude. They should be Gaussian, following the familiar bell curve distribution, and they should be adiabatic, affecting all types of matter and radiation equally. Measurements of the cosmic microwave background by satellites such as COBE, WMAP, and Planck have confirmed these predictions with remarkable precision, providing strong support for the inflationary paradigm. Inflation also predicts the production of gravitational waves, ripples in the fabric of spacetime, generated by the violent dynamics of the inflationary epoch. These primordial gravitational waves would leave a distinctive imprint on the cosmic microwave background, a pattern of polarization called B modes that cosmologists have been searching for with increasingly sensitive instruments. The detection of primordial B modes would provide powerful evidence for inflation and reveal information about the energy scale at which inflation occurred. As of now, this signal has not been definitively detected, but the search continues with ever-improving technology. The inflationary epoch lasted for an almost inconceivably brief time, perhaps 10 to the negative 32 seconds, or even less. Yet in that fleeting interval, the universe underwent transformations of staggering magnitude. Space expanded by a factor that dwarfs any number encountered in everyday life, solving the horizon and flatness problems in a single stroke. The seeds of all cosmic structure were planted through quantum fluctuations stretched to macroscopic scales. Unwanted relics like magnetic monopoles were diluted to negligible densities. The stage was set for the hot Big Bang and all that would follow. As inflation ended, the energy stored in the inflaton field was released, reheating the universe to temperatures comparable to those at the end of the grand unified epoch. The cosmos was filled once again with a hot, dense plasma of particles and radiation, ready to begin the next phase of its evolution. The fundamental forces had differentiated, the geometry of space had been flattened, and the quantum seeds of structure had been sown. From this point forward, the story of the universe would unfold according to the well-tested laws of particle physics and cosmology, a story we can tell with increasing confidence and detail. Let your mind rest now on the image of this cosmic expansion, space stretching faster than light, carrying the seeds of everything that would ever exist. There is something both humbling and exhilarating in this picture, a sense of our own smallness against the vastness of cosmic history, and yet also a sense of connection, of belonging to something far greater than ourselves. The atoms in your body were forged in stars, but the pattern of those stars was set during inflation, written into the fabric of space by quantum fluctuations in the first moment of time. Section 6. The quark epoch and particle formation. As inflation drew to its close and the universe reheated, a new chapter in cosmic history began. The energy stored in the inflaton field flooded into space, creating a seething plasma of particles and radiation at temperatures exceeding 10 to the 27 degrees Kelvin. This was the beginning of the quark epoch, a period lasting from about 10 to the negative 12 seconds until approximately 10 to the negative 6 seconds after the Big Bang. During this time, the fundamental building blocks of matter existed in a state unlike anything found in the universe today, a primordial soup of quarks and gluons, too hot and dense to form the protons and neutrons that would later constitute atomic nuclei. Let us wade gently into this ancient cosmic ocean, exploring its strange and wonderful properties as we continue our journey through time. To understand the quark epoch, we must first acquaint ourselves with the particles that populated this early universe. The standard model of particle physics, developed over the latter half of the 20th century, describes the fundamental constituents of matter and the forces that govern their interactions. According to this model, all ordinary matter is made of two types of particles, quarks and leptons. Quarks come in 6 varieties, whimsically named up: down, charm, strange, top and bottom. Leptons also come in 6 varieties: the electron, muon and tau, along with their associated neutrinos. These 12 matter particles, along with their antimatter counterparts and the force-carrying bosons, constitute the complete inventory of fundamental particles in the Standard Model. In the everyday world, we never encounter isolated quarks. They are always bound together in composite particles called hadrons, held together by the strong force carried by particles called gluons. The most familiar hadrons are protons, made of 2 up quarks and 1 down quark, and neutrons, made of 1 up quark and 2 down quarks. These particles form the nuclei of atoms, which combine with electrons to create the chemical elements that make up everything we see around us. The strong force that binds quarks together is aptly named. It is the strongest of the 4 fundamental forces, powerful enough to overcome the electromagnetic repulsion between the positively charged protons in an atomic nucleus. But in the extreme conditions of the quark epoch, the strong force behaved very differently than it does today. At the enormous temperatures and densities that prevailed, quarks and gluons existed in a state called a quark-gluon plasma, moving freely rather than being confined within hadrons. This state of matter is sometimes described as the most perfect fluid ever observed, flowing with almost no viscosity or internal friction. It existed throughout the universe during the quark epoch, a cosmic ocean of fundamental particles interacting through all 4 forces. The quark-gluon plasma has been recreated in miniature at particle accelerators such as the relativistic heavy ion collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN. By colliding heavy nuclei like gold or lead at nearly the speed of light, physicists can create tiny droplets of quark-gluon plasma that exist for only the briefest instants before cooling and condensing into ordinary hadrons. These experiments have revealed surprising properties of this exotic state of matter, including its remarkably low viscosity and its tendency to flow collectively like a liquid rather than expanding like a gas. During the quark epoch, the universe was a maelstrom of particle creation and annihilation. The intense energy of the environment meant that particle-antiparticle pairs were constantly being created from pure energy and then annihilating back into radiation. Quarks and antiquarks, electrons and positrons, and all the other particles and antiparticles of the Standard Model appeared and disappeared in an endless dance of creation and destruction. The average particle existed for only a tiny fraction of a second before encountering its antiparticle partner and vanishing in a flash of energy, only to be replaced by new particles created from that same energy. This equilibrium between matter and radiation was maintained by the extreme temperature of the universe. As long as the thermal energy exceeded the rest mass energy of a particle type, that particle could be freely created from the ambient radiation. The relationship between mass and energy, expressed in Einstein's famous equation E equals mc squared, meant that the hot early universe contained all the particles that could be created with the available energy. As the universe expanded and cooled, heavier particles became increasingly rare, their creation requiring more energy than the cooling universe could provide. One of the deepest mysteries of the quark epoch concerns the asymmetry between matter and antimatter. According to everything we know about particle physics, the Big Bang should have produced exactly equal amounts of matter and antimatter. The laws governing particle interactions show almost perfect symmetry between matter and antimatter, treating them as mirror images of each other. Yet the universe we observe is made almost entirely of matter, with antimatter appearing only in trace amounts produced by high-energy processes. This cosmic asymmetry requires explanation. The excess of matter over antimatter was tiny, about 1 part in a billion. For every billion antiquarks in the early universe, there were 1,000,000,001 quarks. When the universe cooled enough for matter and antimatter to annihilate without being replaced, this vast annihilation left behind only that tiny excess. The energy released in this annihilation produced the photons that would eventually become the cosmic microwave background radiation. The matter that remained, that 1 part in a billion, is the matter from which everything in the observable universe is made. Every star, every planet, every living thing owes its existence to this slight imbalance in the early universe. The origin of this matter-antimatter asymmetry, a process called baryogenesis, remains one of the outstanding puzzles in cosmology. Several mechanisms have been proposed, including processes during the grand unified epoch that we discussed earlier, and processes during the electroweak epoch that we will encounter shortly. The physicist Andrei Sakharov identified 3 conditions necessary for baryogenesis: violation of baryon number conservation, violation of charge parity symmetry, and departure from thermal equilibrium. Various theories propose different ways these conditions might have been satisfied, but the precise mechanism remains uncertain. As the quark epoch progressed, the universe continued to expand and cool. The temperature dropped from around 10 to the 27 degrees Kelvin at the beginning to about 10 to the 12 degrees Kelvin at the end, still unimaginably hot by everyday standards, but cool enough for significant changes to occur. During this cooling, the universe passed through several important transitions as different particle species dropped out of equilibrium. One such transition involved the electroweak force, which remained unified until the universe cooled to about 10 to the 15 degrees Kelvin, roughly 100 times hotter than the core of the Sun. At this temperature, the electroweak symmetry broke and the electromagnetic and weak forces became distinct. This symmetry breaking gave mass to the W and Z bosons, the carriers of the weak force, while leaving the photon massless. It also gave mass to the fundamental fermions through their interaction with the Higgs field, the field associated with the famous Higgs boson discovered at CERN in 2012. The electroweak phase transition may have been a dramatic event, possibly involving the formation of bubbles of the new broken symmetry phase expanding through the old symmetric phase, like bubbles forming in boiling water. Some theories suggest that this transition could have been a source of baryogenesis, with the asymmetry between matter and antimatter generated at the boundaries of these expanding bubbles. The details depend on aspects of particle physics that remain uncertain, and the electroweak baryogenesis scenario requires extensions to the standard model that have not yet been confirmed experimentally. Another important development during the quark epoch was the decoupling of neutrinos from the rest of the cosmic plasma. Neutrinos are ghostly particles that interact only through the weak force and gravity, making them extremely difficult to detect. In the hot early universe, weak interactions were frequent enough to keep neutrinos in equilibrium with other particles. But as the universe cooled and expanded, weak interactions became increasingly rare, and eventually the neutrinos decoupled, streaming freely through the cosmos without further interaction. This neutrino decoupling occurred when the universe was about 1 second old and the temperature had dropped to about 10 billion degrees Kelvin. The neutrinos released at this time are still present in the universe today, forming a cosmic neutrino background analogous to the cosmic microwave background. However, because neutrinos interact so weakly with matter, this background has never been directly detected, though its existence is inferred from its effects on other cosmological observables. The cosmic neutrino background represents the oldest signal we could potentially detect from the early universe, predating the cosmic microwave background by hundreds of thousands of years. The quark epoch came to an end when the universe had cooled to about 2 trillion degrees, Kelvin roughly 100,000 times hotter than the core of the Sun. At this temperature, a remarkable transition occurred. The quark-gluon plasma condensed into hadrons, with quarks becoming permanently confined within protons, neutrons, and other composite particles. This transition, called the QCD phase transition or hadronization, marked the end of the era when quarks roam freely and the beginning of the hadronic epoch. The QCD phase transition was driven by the peculiar behavior of the strong force at different energy scales. At high energies, the strong force becomes weaker, a property called asymptotic freedom that earned its discoverers the Nobel Prize in 2004. This weakening allowed quarks to move freely in the quark-gluon plasma. But at lower energies, the strong force becomes stronger, eventually becoming so powerful that quarks cannot escape from hadrons. The transition between these regimes occurred when the universe cooled below the QCD scale, about 200 million electron volts. During hadronization, quarks combined in groups of 3 to form baryons like protons and neutrons, or in quark-antiquark pairs to form mesons like pions. The specific combinations were determined by the rules of quantum chromodynamics, the theory of the strong force. Only combinations that are color neutral, with the color charges of the constituent quarks cancelling out, can exist as free particles. This requirement explains why we never see isolated quarks or combinations of 2 or 4 quarks in nature. The hadronization process also saw the annihilation of most of the matter and antimatter that had survived to this point. Protons and antiprotons, neutrons and antineutrons annihilated in vast numbers, converting their mass into energy. Only the tiny excess of matter over antimatter remained, the 1 part in a billion that would become the atoms of the universe. The energy released in this annihilation added to the radiation filling the cosmos, contributing to the photon bath that would eventually become the cosmic microwave background. As the hadronic epoch began, the universe was filled with a hot plasma of protons, neutrons, electrons, photons, and neutrinos. The temperature was still billions of degrees, far too hot for atomic nuclei to form, but the fundamental building blocks of ordinary matter were now in place. The stage was set for the next great transformation. Nucleosynthesis, the forging of the first atomic nuclei in the cosmic furnace. This process would determine the chemical composition of the universe, setting the proportions of hydrogen, helium, and other light elements that we observe today. Let your thoughts drift now through this ancient cosmic plasma, imagining the ceaseless activity of particles appearing and disappearing, combining and separating in a dance choreographed by the fundamental forces of nature. The universe at this stage was simpler than it would later become, containing only a handful of particle types interacting according to well-understood rules. Yet from this simplicity, all the complexity of the cosmos would eventually emerge, as gravity gathered matter into stars and galaxies, as nuclear reactions forged heavy elements, as chemistry built molecules of ever-increasing intricacy, and as life arose to contemplate its own origins. The quark epoch and its aftermath remind us that the familiar world of atoms and molecules is not fundamental but emergent, arising from deeper levels of physical reality. The protons in your body are not elementary particles, but composite objects, each containing 3 quarks bound together by gluons. These quarks have existed since the quark epoch, surviving the Great Annihilation and the hadronization transition to become part of the matter that makes up everything we see. In a very real sense, you are made of quark epoch relics, ancient particles that have journeyed through billions of years of cosmic history to become part of you. Section 7. Nucleosynthesis forging the first element. C. As the universe continued its relentless expansion and cooling, it entered a period of remarkable creativity, a cosmic forge in which the first atomic nuclei were assembled from the protons and neutrons that had emerged from the quark epoch. This process, known as Big Bang nucleosynthesis or primordial nucleosynthesis, occurred during a narrow window of time when conditions were just right for nuclear reactions to proceed. Too early, and the intense radiation would have blasted apart any nuclei that tried to form. Too late, and the universe would have become too cool and diffuse for nuclear reactions to occur at all. In this brief interval, lasting from about 10 seconds to roughly 20 minutes after the Big Bang, the universe forged the light elements that would become the raw material for everything that followed. Let us explore this cosmic alchemy together, tracing the delicate dance of particles that determine the chemical composition of the primordial universe. To understand nucleosynthesis, we must first appreciate the conditions that prevailed in the universe during this epoch. The temperature had dropped to about 10 billion degrees Kelvin at the beginning of nucleosynthesis, roughly 1,000 times hotter than the core of the Sun. This is still extraordinarily hot by any everyday standard, but it was cool enough for nuclear reactions to begin building complex nuclei from individual protons and neutrons. The universe was filled with a dense plasma of these particles, along with electrons, positrons, photons, and neutrinos, all interacting furiously in the cosmic furnace. The story of nucleosynthesis begins slightly earlier, during the first second of cosmic history, when the ratio of protons to neutrons was being established. Protons and neutrons can convert into each other through weak interactions involving electrons, positrons, and neutrinos. At very high temperatures, these reactions occurred rapidly enough to maintain equilibrium between protons and neutrons, with slightly more protons because they are slightly lighter and therefore energetically favoured. As the universe cooled, these weak reactions became slower, and eventually they could no longer keep pace with the expansion. When the temperature dropped to about 10 billion degrees, roughly 1 second after the Big Bang, the weak interactions froze out, and the ratio of neutrons to protons became fixed at about 1 neutron for every 7 protons. This ratio would have important consequences for the final abundances of the light elements. From this point on, the only change in the neutron to proton ratio came from the radioactive decay of free neutrons, which have a half-life of about 10 minutes. Neutrons bound inside nuclei are stable, protected from decay by the nuclear binding energy, so the race was on to incorporate neutrons into nuclei before they could decay away. The first step in building heavier nuclei is the formation of deuterium, also known as heavy hydrogen. A deuterium nucleus consists of 1 proton and 1 neutron bound together, the simplest possible nucleus containing more than 1 particle. The reaction that forms deuterium is straightforward. A proton and a neutron collide and stick together, releasing a gamma-ray photon that carries away the excess energy. This reaction occurred readily in the early universe, but there was a problem. Deuterium nuclei are fragile, easily broken apart by high-energy photons. In the intense radiation field of the early universe, deuterium was destroyed almost as fast as it was created. This bottleneck, sometimes called the deuterium bottleneck, prevented nucleosynthesis from proceeding until the universe had cooled enough for deuterium to survive. The critical temperature was about 1 billion degrees Kelvin, reached when the universe was roughly 3 minutes old. Below this temperature, the photons in the cosmic radiation field no longer had enough energy to efficiently destroy deuterium, and the deuterium abundance began to build up. Once deuterium became abundant, the subsequent nuclear reactions could proceed rapidly, racing to completion before the universe became too cool and diffuse. With deuterium available as a stepping stone, heavier nuclei could form through a series of reactions. Deuterium could capture another proton to form helium-3, a light isotope of helium with 2 protons and 1 neutron. Alternatively, deuterium could capture a neutron to form tritium, a heavy isotope of hydrogen with 1 proton and 2 neutrons. These intermediate nuclei could then combine with each other, or with additional protons and neutrons, to form helium-4, the common isotope of helium with 2 protons and 2 neutrons. Helium-4 is an exceptionally stable nucleus, with all 4 of its particles arranged in a particularly favourable configuration. The binding energy of helium-4 is much greater than that of the lighter nuclei, making it the natural endpoint of primordial nucleosynthesis. Once helium-4 formed, it was very difficult to build heavier elements, because there are no stable nuclei with 5 or 8 particles. This gap in the nuclear stability landscape meant that reactions adding a proton or neutron to helium-4 produced unstable nuclei that quickly fell apart. Similarly, reactions combining 2 helium-4 nuclei produced beryllium-8, which is so unstable that it disintegrates in less than a billionth of a second. Despite these obstacles, trace amounts of heavier elements did form during Big Bang nucleosynthesis. A small fraction of helium-3 and tritium captured additional particles to form lithium-7, an isotope of lithium with 3 protons and 4 neutrons. Even smaller amounts of beryllium-7, which later decays into lithium-7, were produced. But the abundances of these heavier elements were tiny compared to hydrogen and helium, measured in parts per billion rather than percent. The overwhelming majority of the matter emerging from nucleosynthesis was hydrogen, about 75% by mass, with most of the remainder being helium-4, about 25% by mass. These predicted abundances are one of the great triumphs of Big Bang cosmology, matching observations of the primordial composition of the universe with remarkable precision. The abundance of helium in ancient, chemically primitive stars and gas clouds agrees beautifully with the predictions of nucleosynthesis calculations. The abundance of deuterium, measured in distant gas clouds, illuminated by quasars, also matches predictions when the density of ordinary matter in the universe is properly accounted for. Even the tiny abundance of lithium-7, though there are some discrepancies that remain under investigation, broadly confirms the nucleosynthesis picture. The success of Big Bang nucleosynthesis in predicting the abundances of light elements provides powerful evidence that our understanding of the early universe is fundamentally correct. The calculations involve well-tested nuclear physics applied to conditions that we can specify from cosmological observations. The agreement between prediction and observation tells us that the universe really was hot and dense in its early moments, that it expanded and cooled according to the equations of general relativity, and that the nuclear reactions we study in laboratories on Earth governed the formation of the first elements billions of years ago. Nucleosynthesis also provides important constraints on the properties of the universe. The abundances of the light elements depend sensitively on the density of ordinary matter, the number of neutrino species, and other cosmological parameters. By comparing observed abundances with theoretical predictions, cosmologists can determine these parameters with considerable precision. The results confirm that ordinary matter, the stuff of atoms and molecules, makes up only about 5% of the total energy density of the universe. The rest consists of dark matter and dark energy, mysterious components whose nature remains one of the great puzzles of modern physics. The nuclear reactions of Big Bang nucleosynthesis were essentially complete by the time the universe was about 20 minutes old. After this point, the temperature and density had dropped too low for nuclear reactions to proceed at significant rates. The composition of the universe was frozen in, locked into the proportions that had been established during that brief window of nuclear activity. For the next several 100,000 years, the universe would expand and cool without significant chemical change. A vast ocean of hydrogen and helium plasma, slowly approaching the conditions necessary for the next great transformation. It is worth pausing to appreciate the remarkable precision of this cosmic chemistry. The abundances of the light elements depend on a delicate balance of nuclear reaction rates, expansion rates, and initial conditions. If the universe had expanded faster, there would have been less time for nuclear reactions, resulting in more hydrogen and less helium. If it had expanded slower, more helium and possibly heavier elements would have formed. If the ratio of neutrons to protons had been different, or if the nuclear binding energies had been different, the outcome would have been entirely changed. The fact that our universe produced the particular mix of elements that it did is a consequence of the specific values of the fundamental constants and the specific conditions of the Big Bang. Some physicists have noted that these values seem remarkably well suited for the eventual emergence of complexity and life. If the universe had produced only hydrogen, stars would burn differently, and the heavy elements necessary for planets and life might never have formed. If it had produced mostly helium or heavier elements, the universe would also look very different, possibly in ways incompatible with our existence. This observation has led to discussions of the anthropic principle, the idea that the properties of the universe must be compatible with the existence of observers like us. Whether this represents a deep insight into the nature of reality or merely a selection effect remains a matter of philosophical debate. As nucleosynthesis concluded, the universe settled into a period of relative calm. The nuclear fires had burned out, leaving behind a plasma of hydrogen and helium nuclei, electrons, photons, and neutrinos. This plasma was still far too hot for atoms to form. Any electron that tried to bind to a nucleus was quickly knocked free by the intense radiation. The photons, trapped in a cosmic dance of absorption and emission, could not travel far before interacting with the charged particles of the plasma. The universe was opaque, filled with a glowing fog that would persist for hundreds of thousands of years. Let your mind rest now on this image of the primordial cosmos, a vast ocean of simple elements forged in the first minutes of time. The hydrogen and helium that emerged from nucleosynthesis would become the raw material for everything that followed. The first stars, the first galaxies, and eventually the heavier elements that make up planets and living things. Every atom of hydrogen in your body, in the water you drink, and the organic molecules of your cells dates back to this epoch, forged in the cosmic furnace of the Big Bang. You are, quite literally, made of primordial material, ancient beyond measure, yet intimate and personal. Section 8. The Cosmic Dark Ages and Recombination. Following the fury of nucleosynthesis, the universe entered a long period of gradual cooling and expansion, a cosmic twilight that would last for hundreds of thousands of years. During this time, the universe remained a hot, dense plasma, with matter and radiation tightly coupled in a state of thermal equilibrium. Photons scattered constantly off the free electrons that filled space, unable to travel more than a short distance before being absorbed and re-emitted. The universe was opaque, glowing with the light of its own heat but revealing nothing of its internal structure. This period would eventually give way to one of the most important transitions in cosmic history: recombination, when atoms formed for the first time and the universe became transparent. Let us journey together through this long cosmic twilight, following the universe as it cooled toward this momentous transformation. In the immediate aftermath of nucleosynthesis, the temperature of the universe was still measured in billions of degrees, and the plasma filling space was extraordinarily hot and dense. As the universe expanded, both the temperature and density decreased, following the inexorable logic of cosmic expansion. The photons that filled space were stretched along with the expanding space itself, their wavelengths increasing and their energies decreasing. What had been gamma rays became X-rays, then ultraviolet light, then visible light, then infrared, in a continuous process of cosmic cooling. Throughout this period, the universe remained in a state of thermal equilibrium, with matter and radiation sharing a common temperature. The photons were so numerous and so energetic that they dominated the energy density of the universe, a condition called radiation domination. The expansion rate of the universe during this epoch was determined primarily by the radiation, with matter playing a secondary role. This would eventually change as the universe continued to cool, but for now, radiation was king. The coupling between matter and radiation was maintained by the constant scattering of photons of free electrons. This process, called Thomson scattering, is the same mechanism that makes clouds white and milk opaque. When a photon encounters a free electron, it bounces off in a random direction, transferring some of its energy to the electron in the process. In the early universe, this scattering happened so frequently that photons could not travel far before being redirected, creating the opaque fog that filled the cosmos. This opacity had important consequences for the evolution of structure in the universe. The tiny density fluctuations that had been planted during inflation, the seeds of future galaxies and clusters, could not grow freely during the radiation-dominated era. When matter tried to clump together under its own gravity, the radiation pressure from the tightly coupled photons pushed back, preventing the growth of structure. The fluctuations oscillated like sound waves in the cosmic plasma, with gravity pulling matter inward and radiation pressure pushing it outward. These oscillations, called baryon acoustic oscillations, would leave their imprint on the cosmic microwave background and on the distribution of galaxies in the universe today. As the universe continued to expand and cool, it gradually approached a critical threshold. The photons, stretched to ever longer wavelengths, became less and less energetic. Eventually, they would no longer have enough energy to ionize hydrogen atoms, to knock electrons free from protons. When this happened, electrons would be able to bind to nuclei for the first time, forming neutral atoms. This transition, somewhat confusingly called recombination, even though the electrons and nuclei had never been combined before, would transform the universe from an opaque plasma to a transparent gas. The recombination epoch occurred when the universe was approximately 380,000 years old, and the temperature had dropped to about 3,000 degrees Kelvin, roughly half the temperature of the surface of the Sun. At this temperature, the photons no longer had enough energy to keep hydrogen ionized, and electrons began to settle into bound orbits around protons. The process was not instantaneous, but occurred over a period of roughly 100,000 years, as the universe cooled through the critical temperature range. As neutral atoms formed, the free electron density dropped rapidly, and photons found themselves able to travel farther and farther without scattering. The universe transitioned from opaque to transparent, like a fog lifting to reveal a clear sky. The photons that had been trapped in the cosmic plasma were suddenly free to stream across the universe, travelling in straight lines for billions of years until they reached distant observers. These photons, released at the moment of recombination, are what we detect today as the cosmic microwave background radiation. The cosmic microwave background is one of the most important observational tools in cosmology, a snapshot of the universe as it appeared 380,000 years after the Big Bang. When we observe the CMB, we are looking back through time to the surface of last scattering, the moment when photons last interacted with matter before beginning their long journey to our detectors. This surface is like a cosmic baby picture, showing the universe in its infancy, long before stars or galaxies had formed. The CMB is remarkably uniform, with the same temperature in every direction to within a few parts in 100,000. This uniformity reflects the thermal equilibrium that prevailed before recombination, when matter and radiation were tightly coupled and any temperature differences were quickly smoothed out. The tiny variations that do exist, the anisotropies in the CMB, are the imprints of the primordial density fluctuations, the seeds of cosmic structure that were planted during inflation. These anisotropies have been measured with exquisite precision by a series of increasingly sophisticated experiments. The Cosmic Background Explorer satellite, launched in 1989, first detected the anisotropies and confirmed that the CMB has a perfect blackbody spectrum, exactly as predicted by the Big Bang theory. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the anisotropies with much greater precision, revealing detailed information about the composition and geometry of the universe. The Planck satellite, launched in 2009, improved on these measurements still further, providing our current best picture of the infant universe. The pattern of anisotropies in the CMB encodes a wealth of information about the early universe. The angular size of the fluctuations tells us about the geometry of space, confirming that the universe is very close to flat. The relative heights of different peaks in the power spectrum reveal the proportions of ordinary matter, dark matter, and dark energy. The polarization of the CMB light provides additional information about the conditions at recombination and potentially about the gravitational waves produced during inflation. Cosmologists have extracted an astonishing amount of information from this ancient light, building a detailed and precise model of the universe and its history. Following recombination, the universe entered a period known as the Cosmic Dark Ages. With the primordial plasma transformed into neutral gas, there were no sources of light in the universe. The cosmic microwave background, though still present, had been redshifted to longer and longer wavelengths as the universe expanded, fading from visible light to infrared to microwave. The universe was filled with a cold, dark gas of hydrogen and helium, slowly cooling and gradually beginning to clump together under the influence of gravity. The Dark Ages lasted for roughly 100 to 200 million years, a vast span of time during which very little happened from an observational standpoint. The universe expanded and cooled. The density fluctuations slowly grew under gravitational attraction, and the stage was set for the formation of the first luminous objects. But there were no stars to shine, no galaxies to glow, no sources of light to break the cosmic darkness. If any observer had existed during this period, they would have seen nothing but blackness, an empty void stretching in every direction. Yet beneath this apparent emptiness, profound changes were taking place. The tiny density fluctuations that had been imprinted during inflation, preserved through the radiation-dominated era as acoustic oscillations, were now free to grow. Without the radiation pressure that had previously opposed gravitational collapse, matter could begin to clump together, falling into the gravitational wells created by the initial fluctuations. Dark matter, which does not interact with light and was therefore unaffected by radiation pressure, had already begun this process, forming the first gravitational structures that would eventually host galaxies. The growth of structure during the Dark Ages followed a hierarchical pattern, with smaller structures forming first and then merging to create larger ones. The first objects to collapse under their own gravity were small clumps of dark matter, called mini-halos, with masses perhaps 1 million times that of the Sun. These mini-halos attracted ordinary matter, hydrogen and helium gas that fell into their gravitational wells and began to accumulate. Over time, larger and larger structures formed, building up the cosmic web of filaments and nodes that characterizes the large-scale structure of the universe today. The Dark Ages would eventually end with the formation of the first stars, objects that would transform the universe by flooding it with light and beginning the process of chemical enrichment that would eventually produce the heavy elements necessary for planets and life. But that story belongs to the next chapter of our cosmic journey. For now, let us rest in the darkness of this primordial epoch, contemplating the vast spans of time during which the universe waited in silence for the first light to appear. The cosmic Dark Ages represent a profound transition in the history of the universe. Before recombination, the cosmos was a hot, bright, opaque plasma, with matter and radiation locked together in thermal equilibrium. After recombination, it became a cold, dark, transparent gas, with matter free to clump together under gravity while radiation streamed freely through space. This transition set the stage for everything that would follow, for the formation of stars and galaxies, for the synthesis of heavy elements, for the emergence of planets, and eventually life. As you drift deeper into relaxation, let the image of the Dark Ages settle gently into your mind. Picture the universe as a vast, quiet ocean of hydrogen and helium, stretching endlessly in every direction, with no light to break the darkness and no sound to disturb the silence. Yet within this darkness the seeds of everything beautiful and complex were already present, encoded in the subtle variations of density that would eventually grow into the cosmic structures we observe today. The darkness was not empty, but pregnant with possibility, waiting for the right conditions to bring forth light and life. The cosmic microwave background that we detect today is a messenger from this distant epoch, carrying information about the universe as it was 380,000 years after the Big Bang. When you look at a map of the CMB, you are seeing the oldest light in the universe, photons that have travelled for over 13 billion years to reach our instruments. These ancient photons have witnessed the entire history of cosmic structure formation, passing through the gravitational fields of galaxies and clusters, being slightly deflected and distorted along the way. They carry within them the secrets of the early universe, secrets that cosmologists have only begun to decode. The transition from the hot plasma of the early universe to the cold gas of the Dark Ages was one of the most dramatic transformations in cosmic history. It marked the end of the era when radiation dominated the universe, and the beginning of the era when matter would take center stage. It released the cosmic microwave background, providing us with our most important window into the early universe. And it set the stage for the formation of the first stars and galaxies, the subject of our next chapter. Let your breathing slow and your body relax as we prepare to leave the darkness of the cosmic dark ages and enter the era of first light. The universe has journeyed from the unimaginable heat and density of the Big Bang, through the forging of the first elements, through the release of the cosmic microwave background, to this quiet epoch of darkness and waiting. Soon the first stars will ignite, flooding the universe with light and beginning a new chapter in the cosmic story. But for now, rest in the peaceful darkness, knowing that even in the absence of light, the universe was preparing for the wonders that would follow. Section 9. The First Stars and Cosmic Dawn. After hundreds of millions of years of darkness, the universe stood on the threshold of a profound transformation. The cold, quiet cosmos, filled with nothing but hydrogen and helium gas, slowly gathering under gravity's patient influence, was about to witness the birth of the first stars. These primordial beacons, unlike any stars that exist today, would flood the universe with light for the first time since the cosmic microwave background faded into the infrared. This period, known as cosmic dawn, marks one of the most significant transitions in the history of the universe. The moment when darkness gave way to light and the cosmos began its long journey toward the complexity we observe today. Let us explore this remarkable epoch together, following the universe as it awakened from its long slumber and began to shine. The formation of the first stars required the coming together of several conditions that had been slowly developing throughout the cosmic dark ages. Dark matter, which had been clumping together since long before recombination, had formed a web of gravitational structures throughout the universe. These dark matter halos, ranging from small mini-halos to larger structures, provided the gravitational scaffolding into which ordinary matter could fall. Hydrogen and helium gas, attracted by the gravity of these halos, accumulated in their centers, growing denser and denser over millions of years. For a cloud of gas to collapse and form a star, it must be able to radiate away the heat generated by compression. As gas falls inward under gravity, it gains kinetic energy, which is converted to thermal energy through collisions between particles. If this heat cannot escape, the gas pressure increases, eventually halting the collapse. In the modern universe, gas clouds cool efficiently through radiation from heavy elements like carbon and oxygen, which have many atomic transitions that can emit photons. But in the primordial universe, there were no heavy elements, only hydrogen and helium, which are much less efficient at radiating heat. This cooling problem meant that the first stars formed under very different conditions than stars forming today. The primordial gas clouds had to rely on molecular hydrogen, two hydrogen atoms bound together, to cool. Molecular hydrogen can radiate energy through rotational and vibrational transitions, but it is far less efficient than the atomic cooling provided by heavy elements. As a result, the primordial gas clouds could only cool to temperatures of a few hundred degrees Kelvin, much warmer than the 10-degree temperatures achieved in modern molecular clouds. The higher temperatures in primordial gas clouds had profound consequences for the masses of the first stars. The minimum mass for a self-gravitating gas cloud, called the gene's mass, depends on the temperature of the gas. Higher temperatures mean higher pressures, which require larger masses to overcome. Calculations suggest that the first stars, often called population 3 stars, were much more massive than typical stars today, perhaps ranging from tens to hundreds of times the mass of our Sun. Some models suggest that individual first stars could have reached masses of several hundred solar masses, far exceeding any star observed in the modern universe. These massive primordial stars would have been extraordinary objects by any standard. Their surface temperatures would have reached 100,000 degrees, Kelvin or more, several times hotter than the surface of our Sun. They would have glowed with an intense blue-white light, pouring out prodigious amounts of ultraviolet radiation. Their luminosities would have exceeded that of our Sun by millions of times, making them visible across vast cosmic distances despite their isolation in the early universe. Yet for all their brilliance, they would have been lonely beacons, scattered sparsely through a cosmos still mostly dark and empty. The first stars are thought to have formed when the universe was roughly 100 to 200 million years old, though the exact timing remains uncertain. The process began in the densest regions of the cosmic web, where dark matter halos had accumulated enough gas to trigger gravitational collapse. A typical first star might have formed in a mini-halo with a total mass of about 1 million solar masses, with only a small fraction of that mass consisting of the ordinary matter that would actually become the star. The collapse would have taken millions of years, with the gas slowly settling toward the centre of the halo, heating up as it fell, and eventually reaching the temperatures and densities necessary to ignite nuclear fusion. When nuclear fusion finally began in the core of a primordial gas cloud, a first star was born. The ignition of hydrogen fusion marked the end of the cosmic dark ages and the beginning of cosmic dawn. Light flooded out from the newborn star, illuminating the surrounding gas and travelling outward into the dark universe. For the first time in hundreds of millions of years, there was a source of light in the cosmos, a beacon shining in the darkness. The ultraviolet radiation from the first stars had a dramatic effect on the surrounding universe. This energetic light was capable of ionizing hydrogen atoms, stripping away their electrons and returning them to the plasma state that had characterized the universe before recombination. As more and more first stars formed, their combined radiation began to ionize the intergalactic medium, creating bubbles of ionized gas that expanded outward from each star. Over time, these bubbles grew and merged, eventually filling the entire universe with ionized gas. This process, called reionization, transformed the universe from a neutral gas back to a plasma, though a much cooler and more diffuse plasma than had existed before recombination. Reionization was a complex and extended process, lasting from roughly 200 million years to about 1 billion years after the Big Bang. It did not happen all at once, but proceeded gradually as more stars formed and their ionizing radiation spread through the cosmos. The intergalactic medium was not uniformly ionized, but developed a patchy structure with ionized bubbles surrounding regions of active star formation and neutral gas persisting in the voids between. Eventually, the ionized regions merged and filled the universe, completing the reionization process and leaving the intergalactic medium in the ionized state we observe today. The first stars lived fast and died young, their enormous masses driving nuclear reactions at furious rates. While our Sun will shine for roughly 10 billion years, a massive first star might have exhausted its nuclear fuel in just a few million years. When the fuel ran out, these stars met dramatic ends, collapsing under their own gravity and exploding as supernovae of unprecedented power. Some of the most massive first stars may have collapsed directly into black holes, while others exploded as pair instability supernova, a type of explosion so violent that it completely destroys the star, leaving no remnants behind. These primordial supernovae were crucial for the chemical evolution of the universe. Throughout their brief lives, the first stars had been fusing hydrogen into helium in their cores, and as they evolved, they fused helium into heavier elements like carbon, oxygen, and silicon. The most massive stars built up layers of progressively heavier elements, like the layers of an onion, with iron at the very centre. When these stars exploded, they scattered these newly forged elements into the surrounding gas, enriching it with the heavy atoms that had not existed since the Big Bang. This process of chemical enrichment, called stellar nucleosynthesis, is the origin of most of the elements in the periodic table. The hydrogen and helium that emerged from the Big Bang were transformed through generations of stellar birth and death into the carbon, oxygen, nitrogen, and other elements that make up planets and living things. Every atom of carbon in your body was forged in the core of a star that lived and died billions of years ago. Every atom of oxygen you breathe was created in the nuclear furnace of a stellar interior. We are, as the astronomer Carl Sagan famously said, made of star stuff. The enrichment of the universe with heavy elements had profound consequences for subsequent star formation. Gas that contained even small amounts of heavy elements could cool much more efficiently than primordial gas, allowing it to fragment into smaller clumps and form lower mass stars. The second generation of stars, called population 2 stars, formed from this enriched gas and were generally less massive than their population 3 predecessors. As more generations of stars lived and died, the heavy element content of the universe gradually increased, eventually reaching the levels we observe today. The transition from population 3 to population 2 star formation marked a fundamental change in the character of the universe. The era of massive isolated first stars gave way to an era of more numerous, lower mass stars forming in increasingly complex environments. Galaxies began to assemble from the mergers of smaller structures, bringing together stars, gas, and dark matter into the large-scale systems we observe today. The universe was becoming richer and more diverse, building the complexity that would eventually give rise to planets, chemistry, and life. Observing the first stars directly remains one of the great challenges of modern astronomy. These objects are so distant that their light has been travelling for over 13 billion years to reach us, and they're so rare and short-lived that detecting them individually may be beyond our current capabilities. However, astronomers have developed indirect methods to study the era of first stars and rhyonisation. The cosmic microwave background carries subtle imprints of rhyonisation, as the ionised gas scattered some of the CMB photons on their way to our detectors. Observations of distant quasars reveal the absorption signatures of neutral hydrogen in the intergalactic medium, allowing astronomers to trace the progress of rhyonisation. And the James Webb Space Telescope, launched in 2021, is probing deeper into the early universe than ever before, searching for the first galaxies and potentially the first stars. The cosmic dawn represents a pivotal moment in the history of the universe, the transition from a simple, dark cosmos to a complex, luminous one. The first stars were the agents of this transformation, flooding the universe with light and seeding it with the heavy elements necessary for the rich chemistry that would follow. Though these primordial beacons have long since faded, their legacy persists in every star, every planet, and every living thing in the universe today. We are the descendants of the first stars, inheritors of their light and their atoms, participants in a cosmic story that began with their ignition billions of years ago. As you rest and let these ideas wash over you, imagine the universe at the moment of cosmic dawn. Picture the darkness giving way to light as the first stars ignited, scattered points of brilliance appearing in the vast cosmic void. Feel the warmth of that first starlight, the photons streaming outward through space that had been dark for hundreds of millions of years. The universe was waking up, beginning its long journey toward the complexity and beauty we observe today. And in that awakening, the seeds of everything we know and love were being planted, waiting to grow through billions of years of cosmic evolution. Section 10. Galaxy formation and large-scale structure. With the first stars blazing in the cosmic darkness and the process of reionization transforming the intergalactic medium, the universe entered a new phase of its evolution. The scattered points of light that marked the first stars began to gather together, drawn by gravity into ever larger structures. Dark matter halos merged and grew, pulling ordinary matter along with them. Gas accumulated in the centers of these halos, cooling and collapsing to form new generations of stars. Over hundreds of millions of years, these processes gave rise to the first galaxies, vast collections of stars, gas, and dark matter bound together by gravity. Let us explore this era of cosmic construction together, following the universe as it built the grand structures that fill the sky today. The formation of galaxies is intimately connected to the nature of dark matter, the mysterious substance that makes up roughly 85% of all matter in the universe. Dark matter does not emit, absorb, or scatter light, making it invisible to our telescopes. Yet its gravitational influence is unmistakable, shaping the motions of stars within galaxies, the movements of galaxies within clusters, and the large-scale distribution of matter throughout the cosmos. Without dark matter, galaxies as we know them could not exist, and the universe would look profoundly different. The role of dark matter in galaxy formation begins long before the first stars appeared. During the cosmic dark ages, while ordinary matter was still coupled to radiation and unable to clump together, dark matter was already forming structures. Free from the radiation pressure that held ordinary matter in check, dark matter particles responded only to gravity, falling together into clumps and filaments. These dark matter structures grew hierarchically, with smaller halos forming first and then merging to create larger ones. By the time the first stars formed, a complex web of dark matter structures already spanned the universe, providing the gravitational framework for galaxy formation. When ordinary matter finally decoupled from radiation at recombination, it began to fall into the gravitational wells created by dark matter. The gas accumulated in the centers of dark matter halos, where it could cool and collapse to form stars. The first galaxies were small and irregular, containing perhaps a few million stars, nothing like the grand spiral and elliptical galaxies we see today. But these proto-galaxies were the building blocks from which all larger structures would eventually be assembled. The growth of galaxies proceeded through a combination of two processes: the accretion of gas from the intergalactic medium and the merging of smaller galaxies into larger ones. Gas flowed into galaxies along the filaments of the cosmic web, providing fresh fuel for star formation. When two galaxies passed close to each other, their mutual gravity could draw them together, eventually merging them into a single, larger galaxy. These mergers were often violent events, triggering bursts of star formation and dramatically reshaping the structures of the galaxies involved. The hierarchical nature of galaxy formation means that the large galaxies we observe today are the products of countless mergers over billions of years. Our own Milky Way galaxy, home to several 100 billion stars, was assembled from the mergers of many smaller galaxies throughout cosmic history. Evidence of these past mergers can be found in the streams of stars that orbit the Milky Way. the remnants of smaller galaxies that were torn apart by our galaxy's gravity. The process continues today, with the Milky Way currently in the process of absorbing several small satellite galaxies, including the Sagittarius dwarf elliptical galaxy. The diversity of galaxy shapes and sizes reflects the variety of histories that different galaxies have experienced. Spiral galaxies like the Milky Way have disc-like structures with graceful spiral arms, the result of relatively quiescent histories with steady gas accretion and ongoing star formation. Elliptical galaxies, by contrast, are more spherical or football-shaped, with older stellar populations and little ongoing star formation. These galaxies are thought to form primarily through major mergers, violent collisions that scramble the ordered disk structures of spiral galaxies into more chaotic elliptical shapes. Irregular galaxies with no clear structure may represent galaxies in the process of merging, or galaxies that have been disturbed by gravitational interactions with neighbours. At the centres of most large galaxies lurk supermassive black holes, objects with masses ranging from millions to billions of times the mass of our Sun. These cosmic monsters are thought to have grown alongside their host galaxies, fed by gas falling into the galactic centre and by mergers with other black holes. When gas falls toward a supermassive black hole, it can form a swirling disk that heats up and glows brilliantly, outshining all the stars in the galaxy combined. These active galactic nuclei, including the extremely luminous objects called quasars, were more common in the early universe, when galaxies were still assembling and gas was more abundant. The relationship between supermassive black holes and their host galaxies is one of the most intriguing puzzles in modern astrophysics. Observations have revealed tight correlations between the masses of supermassive black holes and the properties of their host galaxies, suggesting that the two grow together in some coordinated fashion. The energy released by active galactic nuclei can heat and expel gas from galaxies, potentially shutting off star formation and regulating the growth of the galaxy itself. This feedback between black holes and galaxies is thought to play a crucial role in shaping the galaxy population we observe today. Beyond individual galaxies, the universe displays structure on even larger scales. Galaxies are not distributed randomly through space, but are organized into a vast cosmic web of filaments, walls, and nodes. Galaxy clusters, containing hundreds or thousands of galaxies bound together by gravity, mark the densest nodes of this web. These clusters are the largest gravitationally bound structures in the universe, with total masses reaching quadrillions of times the mass of our Sun. Between the clusters stretch filaments of galaxies, elongated structures that connect the nodes of the cosmic web. And between the filaments lie vast cosmic voids, regions of space nearly empty of galaxies, where the density of matter is far below the cosmic average. The cosmic web is a direct consequence of the primordial density fluctuations that were imprinted during inflation. The pattern of these fluctuations, stretched to cosmic scales by the exponential expansion, determined where matter would eventually accumulate. Regions of slightly higher density attracted more matter through gravity, growing denser over time, while regions of slightly lower density lost matter to their denser neighbours, becoming emptier. Over billions of years, this process of gravitational amplification transformed the subtle variations of the early universe into the dramatic structures we observe today. The study of large-scale structure provides powerful tests of our cosmological models. The distribution of galaxies on large scales carries information about the composition of the universe, the nature of dark matter and dark energy, and the initial conditions set during inflation. Surveys that map the positions of millions of galaxies have revealed the statistical properties of the cosmic web, confirming predictions of the standard cosmological model with remarkable precision. The baryon acoustic oscillations that we discussed earlier, the sound waves that propagated through the early universe, have left their imprint on the distribution of galaxies, providing a standard ruler that astronomers use to measure cosmic distances. The formation of structure in the universe is an ongoing process that continues to this day. Galaxies continue to merge and grow, clusters continue to accumulate matter from their surroundings, and the cosmic web continues to evolve under the influence of gravity. However, the future evolution of structure will be increasingly dominated by dark energy, the mysterious component that is causing the expansion of the universe to accelerate. As dark energy drives galaxies apart faster and faster, the growth of structure will eventually slow and stop. In the distant future, galaxy clusters will become isolated islands in an ever-expanding void, cut off from each other by the accelerating expansion of space. Our own local group of galaxies, which includes the Milky Way, the Andromeda Galaxy, and several dozen smaller galaxies, is gravitationally bound and will remain together even as the universe expands. In fact, the Milky Way and Andromeda are currently approaching each other and will merge in about 4 to 5 billion years, forming a single larger galaxy, sometimes nicknamed Milkdromeda. This merger will be a spectacular event, though it will unfold over hundreds of millions of years, far too slowly for any observer to watch in real time. The stars in the two galaxies are so widely spaced that actual stellar collisions will be rare, but the gravitational interactions will dramatically reshape both galaxies, likely transforming them from spirals into a single elliptical galaxy. The large-scale structure of the universe is one of the most beautiful and awe-inspiring aspects of the cosmos. The cosmic web, with its filaments and voids, its clusters and superclusters, represents the grandest architecture in existence, structures spanning hundreds of millions of light years, built from the gravitational attraction of matter over billions of years. When we observe this structure, we are seeing the cumulative result of cosmic evolution from the earliest moments of the Big Bang to the present day, the physical manifestation of the laws of physics operating on the grandest possible scales. As you relax and let your thoughts drift through these vast cosmic structures, imagine yourself floating through the cosmic web, passing by galaxies and clusters, traversing the great voids between filaments. The universe at this scale is almost incomprehensibly large, yet it is all connected, all part of a single structure that emerged from the tiny fluctuations of the inflationary epoch. Every galaxy you pass, every cluster you encounter, traces its origin back to those primordial seeds, amplified by billions of years of gravitational growth into the magnificent structures you see around you. The story of galaxy formation and large-scale structure is still being written. Astronomers continue to discover new details about how galaxies form and evolve, how supermassive black holes grow and influence their hosts, and how the cosmic web developed over cosmic time. New telescopes and surveys are probing deeper into the universe and further back in time, revealing the earliest stages of galaxy formation and the processes that shape the cosmos we observe today. Each new observation adds to our understanding, filling in details of a story that began with the Big Bang and continues to unfold around us. The universe has come a long way from the hot, dense plasma of its earliest moments. From the quark-gluon soup of the first microseconds to the vast cosmic web of galaxies and clusters, the cosmos has undergone a remarkable transformation, driven by the fundamental forces of nature and the inexorable logic of physical law. The structures we observe today, from the smallest dwarf galaxies to the largest superclusters, are all descendants of the Big Bang, products of nearly 14 billion years of cosmic evolution. And within those structures, on a small rocky planet orbiting an ordinary star in an ordinary galaxy, life has emerged to contemplate its own origins and marvel at the grandeur of the universe. Section 11. The Evidence. How we know the Big Bang happened. Throughout our journey together, we have traced the story of the universe from its earliest conceivable moments to the grand structures that fill the cosmos today. We have explored epochs so brief that they defy comprehension and timescales so vast that they humble the imagination. But how do we know that this story is true? How can we be confident that the universe really did begin in a hot, dense state nearly 14 billion years ago and evolve through the stages we have described? The answer lies in a remarkable convergence of evidence from multiple independent sources, each pointing toward the same cosmic history. Let us explore this evidence together, examining the observations and measurements that have transformed the Big Bang from a speculative hypothesis into one of the best supported theories in all of science. The first and perhaps most intuitive piece of evidence for the Big Bang comes from the observation that the universe is expanding. This discovery, made by Edwin Hubble in the late 1920s, revolutionized our understanding of the cosmos and provided the foundation for modern cosmology. Hubble observed that distant galaxies are moving away from us, and that more distant galaxies are receding faster. This relationship, now known as Hubble's law, is exactly what we would expect if the universe is expanding uniformly, with space itself stretching and carrying galaxies apart. The expansion of the universe is not like an explosion, with galaxies flying outward through pre-existing space. Instead, it is space itself that is expanding, with new space being created between galaxies. This distinction is subtle but important. In an explosion, there is a centre from which everything moves outward, and objects near the edge move faster than objects near the centre. In an expanding universe, there is no centre. Every point sees all other points receding, and the recession velocity depends only on distance, not on any special location. This is precisely what Hubble observed, confirming that the expansion is a property of space itself, rather than motion through space. If the universe is expanding today, then it must have been smaller in the past. Running the expansion backward in time, we can trace the history of the cosmos to earlier and earlier epochs, when galaxies were closer together, when matter was denser, and when temperatures were higher. Continuing this extrapolation, we arrive at a moment when all the matter and energy in the observable universe was concentrated in an extremely hot, dense state. This is the Big Bang, the beginning of the expansion that continues to this day. The rate of expansion, characterized by a quantity called the Hubble constant, tells us how fast the universe is expanding and allows us to estimate its age. Current measurements place the Hubble constant at approximately 70 kilometers per second per megaparsec, meaning that for every megaparsec of distance, galaxies recede about 70 kilometers per second faster. Combined with our understanding of how the expansion rate has changed over time, this gives an age for the universe of approximately 13.8 billion years. This age is consistent with independent estimates from the ages of the oldest stars and globular clusters, providing a reassuring cross-check on our cosmological model. The second major pillar of evidence for the Big Bang is the cosmic microwave background radiation, which we have discussed at length in earlier sections. This faint glow of microwave light fills the entire sky, coming from every direction with almost perfect uniformity. It is the afterglow of the hot, dense plasma that filled the early universe, released when the cosmos cooled enough for neutral atoms to form approximately 380,000 years after the Big Bang. The existence of this radiation was predicted by Big Bang theory before it was discovered, making its detection a powerful confirmation of the theory. The cosmic microwave background has several properties that strongly support the Big Bang model. First, it has a perfect blackbody spectrum, the characteristic distribution of light emitted by an object in thermal equilibrium. This spectrum is exactly what we would expect from a hot, dense plasma that was in thermal equilibrium before the photons were released. The temperature of the blackbody, about 2.7 degrees Kelvin, matches predictions based on the expansion and cooling of the universe since recombination. No other known process can produce such a perfect blackbody spectrum filling the entire sky. Second, the cosmic microwave background is almost perfectly uniform, with the same temperature in every direction to within a few parts in 100,000. This uniformity reflects the thermal equilibrium of the early universe, when matter and radiation were tightly coupled and any temperature differences were quickly smoothed out. The tiny variations that do exist, the anisotropies we discussed earlier, match the predictions of inflationary cosmology and provide detailed information about the composition and geometry of the universe. The pattern of these anisotropies has been measured with exquisite precision by satellites like COBE, WMAP, and Planck, and the results are in remarkable agreement with theoretical predictions. Third, the cosmic microwave background shows a subtle polarization pattern that provides additional evidence for the Big Bang and inflation. Polarization arises from the scattering of photons off electrons in the early universe, and the pattern of polarization carries information about the conditions at the time of recombination. The observed polarization is consistent with predictions and provides independent confirmation of the standard cosmological model. Searches for a particular type of polarization, called B modes, which would be produced by gravitational waves from inflation, continue with increasingly sensitive instruments. The third major pillar of evidence for the Big Bang is the abundance of light elements in the universe. As we discussed in our exploration of nucleosynthesis, the Big Bang theory predicts that the early universe should have produced specific amounts of hydrogen, helium, deuterium, and lithium. These predictions depend on well-understood nuclear physics and on cosmological parameters that can be measured independently. The observed abundances of these elements, measured in ancient stars and gas clouds that have not been significantly enriched by stellar nucleosynthesis, match the predictions with impressive precision. The abundance of helium-4, approximately 25% of the ordinary matter in the universe by mass, is particularly compelling evidence. This amount of helium cannot be explained by stellar nucleosynthesis alone. Stars produce helium through hydrogen fusion, but not nearly enough to account for the observed abundance. The Big Bang, with its brief but intense period of nuclear reactions in the first few minutes, naturally produces the observed helium abundance. Similarly, the observed abundance of deuterium, a fragile isotope that is destroyed rather than created in stars, matches Big Bang predictions when the density of ordinary matter is properly accounted for. The agreement between predicted and observed light element abundances provides powerful evidence that the universe really was hot and dense in its early moments, with temperatures and densities suitable for nuclear reactions. This evidence is independent of the cosmic microwave background and the expansion of the universe, yet it points to the same cosmic history. The convergence of these independent lines of evidence gives us confidence that our understanding of the early universe is fundamentally correct. Beyond these three pillars, additional evidence supports and refines the Big Bang model. The observed large-scale structure of the universe, the cosmic web of galaxies, clusters, and voids matches predictions based on the growth of primordial density fluctuations under gravitational attraction. The statistical properties of this structure, including the baryon acoustic oscillations imprinted by sound waves in the early universe, provide precise measurements of cosmological parameters that are consistent with other observations. The ages of the oldest stars and globular clusters are consistent with a universe that is approximately 13.8 billion years old, as predicted by the Big Bang model. The discovery of the accelerating expansion of the universe in 1998 added a new dimension to our understanding of cosmic history. Observations of distant supernovae revealed that the expansion of the universe is not slowing down, as would be expected if gravity were the only force at play, but speeding up. This acceleration is attributed to dark energy, a mysterious component that fills space and exerts a repulsive gravitational effect. The existence of dark energy was unexpected but has been confirmed by multiple independent observations, including measurements of the cosmic microwave background and large-scale structure. Dark energy now appears to make up approximately 68% of the total energy density of the universe, with dark matter contributing about 27% and ordinary matter only about 5%. The evidence for the Big Bang is not limited to observations of the distant universe. Laboratory experiments have confirmed many of the physical processes that are central to the Big Bang model. Particle accelerators have recreated conditions similar to those in the early universe, producing quark-gluon plasma and studying the behavior of matter at extreme energies. Nuclear physics experiments have measured the reaction rates that govern nucleosynthesis, allowing precise predictions of light element abundances. These laboratory results provide independent confirmation of the physics underlying the Big Bang model. The Big Bang theory has also made successful predictions that were later confirmed by observation. The existence of the cosmic microwave background was predicted before it was discovered. The detailed pattern of anisotropies in the CMB was predicted by inflationary cosmology before it was measured. The abundance of light elements was calculated before precise observations were available. The ability of a theory to make successful predictions is one of the hallmarks of good science, and the Big Bang model has passed this test repeatedly. It is worth acknowledging that the Big Bang model, like all scientific theories, has limitations and unanswered questions. The nature of dark matter and dark energy remains unknown, despite decades of research. The physics of the very earliest moments, before the Planck time, lies beyond the reach of our current theories. The question of what, if anything, preceded the Big Bang remains open. These mysteries do not undermine the Big Bang model, but rather define the frontiers of current research, the places where new discoveries await. The convergence of evidence from multiple independent sources gives us confidence that the Big Bang model captures something true about the history of the universe. The expansion of the cosmos, the cosmic microwave background, the abundance of light elements, the large-scale structure of the universe, and many other observations all point to the same conclusion. The universe began in a hot, dense state approximately 13.8 billion years ago and has been expanding and cooling ever since. This is not merely a hypothesis or a guess, but a well-tested scientific theory supported by a vast body of evidence. As you rest and reflect on this evidence, consider the remarkable achievement it represents. Humans, living on a small planet orbiting an ordinary star in one of hundreds of billions of galaxies, have managed to piece together the history of the entire universe, from its first moments to the present day. We have done this through careful observation, rigorous reasoning, and the patient accumulation of knowledge over generations. The story of the Big Bang is not just a story about the universe, it is also a story about human curiosity and ingenuity, about our ability to understand the cosmos we inhabit. Section 12, The Far Future and Closing Reflections. We have journeyed together from the first instant of cosmic time to the present day, exploring the remarkable transformations that have shaped the universe we inhabit. But the story does not end here. The universe continues to evolve, and its future stretches out before us, vast and largely unknown. In this final section, let us peer into that future, contemplating what lies ahead for the cosmos on timescales that dwarf even the billions of years we have already traversed. And as we conclude our journey, let us reflect on what this grand cosmic story means for us, the brief and fragile beings who have somehow emerged to witness and wonder at it all. The near future of the universe, on timescales of billions of years, is relatively well understood. The sun will continue to shine for another 5 billion years or so, gradually brightening as it ages. In about 1 billion years, this increased luminosity will make Earth uncomfortably warm, eventually rendering our planet uninhabitable. In 5 billion years, the sun will exhaust the hydrogen fuel in its core and begin to evolve into a red giant, swelling to engulf the inner planets, possibly including Earth. Eventually, the sun will shed its outer layers, leaving behind a dense white dwarf that will slowly cool over trillions of years. Meanwhile, the Milky Way galaxy will continue its dance with its neighbours. In approximately 4 to 5 billion years, our galaxy will collide and merge with the Andromeda Galaxy, our nearest large galactic neighbour. This merger will be a spectacular event, though it will unfold over hundreds of millions of years, far too slowly for any observer to watch in real time. The gravitational interactions will reshape both galaxies, likely transforming them from elegant spirals into a single large elliptical galaxy. New bursts of star formation may occur as gas clouds collide and compress, lighting up the merged galaxy with the brilliance of newborn stars. On longer timescales, the fate of the universe is determined by the competition between gravity, which pulls matter together, and dark energy, which drives the expansion of space. Current observations indicate that dark energy is winning this competition, causing the expansion of the universe to accelerate. If this acceleration continues, the future of the cosmos will be profoundly different from its past. In an accelerating universe, distant galaxies will recede from us faster and faster, eventually crossing the cosmic horizon and becoming forever unobservable. The light they emit will never reach us, stretched to infinite wavelengths by the expanding space between us. Over tens of billions of years, the observable universe will shrink, with fewer and fewer galaxies visible in our cosmic neighbourhood. Eventually, only the galaxies of our local group, bound together by gravity, will remain visible, isolated islands in an ever-expanding void. The stars themselves will eventually burn out. The most massive stars, which burn their fuel fastest, will die first, exploding as supernovae or collapsing into black holes. Smaller stars, like red dwarfs, burn their fuel much more slowly and can shine for trillions of years, far longer than the current age of the universe. But even these long-lived stars will eventually exhaust their hydrogen and fade away. In the far future, perhaps 100 trillion years from now, the last stars will die, and the universe will enter a new dark age, illuminated only by the faint glow of cooling stellar remnants. After the stars have died, the universe will be populated by the remnants of stellar evolution, white dwarfs, neutron stars, and black holes. These objects will cool over immense timescales, radiating away their remaining heat into the ever-expanding void. White dwarfs, the cores of dead sun-like stars, will cool from white-hot to red, to infrared, to invisible, becoming black dwarfs over timescales of quadrillions of years. Neutron stars, the ultra-dense remnants of massive stars, will similarly cool and fade. The universe will become cold and dark, a vast emptiness punctuated by the invisible remnants of a once luminous cosmos. Black holes, the most extreme objects in the universe, will persist the longest. But even black holes are not eternal. Through a process called Hawking radiation, discovered theoretically by physicist Stephen Hawking in the 1970s, black holes slowly emit particles and lose mass over time. This process is extraordinarily slow for large black holes. A black hole with the mass of the Sun would take approximately 10 to the 67 years to evaporate, a number so large that it defies comprehension. Supermassive black holes with billions of solar masses would take even longer, perhaps 10 to the 100 years or more. But eventually, given enough time, even the largest black holes will evaporate, disappearing in a final burst of radiation. After the black holes have evaporated, the universe will enter its final state, sometimes called the heat death or the big freeze. In this state, the universe will be a vast, cold, empty expanse with matter and energy spread so thin that nothing interesting can happen. The temperature will approach absolute zero, and the universe will be in a state of maximum entropy, the most disordered state possible. There will be no stars, no planets, no life, no change, just an endless, timeless void stretching forever in all directions. This vision of the far future might seem bleak, but it is important to remember the timescales involved. The heat death of the universe lies unimaginably far in the future, so distant that the entire current age of the universe is less than an eye blink in comparison. Between now and then, there is time for wonders we cannot imagine, for civilizations to rise and fall, for life to spread through the cosmos, for intelligence to contemplate and perhaps even influence the fate of the universe. The far future is not a destination but a distant horizon, one that need not diminish the significance of the present. There are also alternative scenarios for the fate of the universe, depending on the nature of dark energy and other factors that remain uncertain. If dark energy increases in strength over time, the expansion of the universe could accelerate so dramatically that it tears apart galaxies, stars, planets, and eventually atoms themselves in a scenario called the Big Rip. If dark energy decreases or reverses, the expansion could slow and eventually reverse, leading to a big crunch in which the universe collapses back to a hot, dense state, perhaps triggering a new Big Bang and a new cosmic cycle. These scenarios remain speculative, but they remind us that the future of the universe is not yet written, that there is still much we do not know about the cosmos and its ultimate fate. As we conclude our journey through the story of the Big Bang, let us pause to reflect on what we have learned and what it means for us. We have traced the history of the universe from its first instant to the present day, from the unimaginable heat and density of the Planck epoch to the vast cosmic web of galaxies and clusters. We have seen how the fundamental forces differentiated, how matter formed from energy, how the first elements were forged, how atoms combined, how stars ignited, how galaxies assembled, and how the universe evolved into the complex and beautiful cosmos we observe today. This story is remarkable not only for its content, but for the fact that we know it at all. Humans are small and brief, our lives measured in decades, our civilizations in millennia. Yet we have managed to piece together the history of a universe that is nearly 14 billion years old, to understand processes that occurred in the first fractions of a second, to predict the fate of the cosmos trillions of years in the future. This is a testament to the power of human curiosity and intelligence, to our ability to ask questions and seek answers, to build instruments and develop theories, to test our ideas against the evidence of the natural world. The story of the Big Bang also reveals our deep connection to the cosmos. The atoms in your body were forged in the hearts of stars that lived and died billions of years ago. The hydrogen in the water you drink was created in the first minutes after the Big Bang. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of these were synthesized in stellar interiors and scattered across the galaxy by supernova explosions. You are made of star stuff, as Carl Sagan so eloquently put it, a temporary arrangement of matter that has been part of the universe since its beginning. This connection extends beyond chemistry to the very structure of the cosmos. The density fluctuations that were imprinted during inflation, tiny quantum variations stretched to cosmic scales, grew over billions of years into the galaxies and clusters we observe today. One of those galaxies is the Milky Way, and within it one of those stars is our Sun, and around it one of those planets is Earth. The chain of causation stretches back to the first moments of the universe, connecting you to the Big Bang through an unbroken sequence of physical processes. You are not separate from the cosmos, but part of it, a way for the universe to know itself. As you drift towards sleep, let these thoughts settle gently into your mind. The universe is vast beyond comprehension, ancient beyond imagination, and filled with wonders we are only beginning to discover. Yet it is also intimate and personal, woven into the fabric of your being, present in every atom of your body and every thought in your mind. The story of the Big Bang is your story, the story of how you came to be, the story of the cosmos that gave you birth. The night sky, if you could see it now, is filled with the light of distant stars and galaxies, photons that have travelled for millions or billions of years to reach your eyes. Some of that light began its journey before the Earth existed, before the Sun ignited, before the Milky Way had fully formed. When you look at the stars, you're looking back through time, witnessing the history of the universe written in light across the darkness of space. And somewhere out there, beyond the farthest galaxies we can see, the universe continues to expand, carrying the light of distant stars ever farther away. The cosmic horizon recedes, the void grows, and the future stretches out before us, vast and unknown. What wonders await discovery? What mysteries remain to be solved? What new chapters will be added to the story of the cosmos? These questions are for another time, another journey. For now, let yourself rest, cradled by the gentle gravity of the earth, warmed by the light of a star that has shone for nearly 5 billion years, breathing air that was exhaled by ancient forests and recycled through countless living things. You are part of the cosmic story, a brief but precious chapter in the long history of the universe. Thank you for joining me on this journey through the story of the Big Bang. From the first instant of time to the far reaches of the cosmic future, we have explored the grandest story ever told, the story of everything that is, was, and ever will be. May this knowledge bring you peace, may this wonder bring you joy, and may you rest now in the embrace of a universe that has been preparing for your existence since the very beginning. If you enjoyed this journey through cosmic history, please consider liking this video and subscribing to the channel for more explorations of the wonders of the universe. Your support helps us continue creating content that celebrates the beauty and mystery of the cosmos. Sweet dreams, fellow traveller, and may the stars watch over you as you sleep.